Good afternoon, everyone. Welcome to the Texas Space Grant Consortium's Design Challenge Showcase for Fall 2020. My name is Tim Urban, and I'm the director of the Texas Space Grant Consortium. Joining me online from Texas Space Grant are Talia Jurgens and Angelica Cruzingo. We are happy to be able to continue to host the Design Challenge Showcase in this virtual environment, given the social distancing measure currently in place. During today's broadcast, if you have any questions, please send an email to the address shown at the bottom of your screen, showcase2020@tsgc.utexas.edu, and one of us will respond as soon as we can. Whether you are new to the showcase or have attended regularly for the past 18 years, we hope you enjoy today and join us in celebrating the accomplishments of these talented students. For those joining from YouTube, from outside of Texas and the Space Grant community, let me briefly explain what Texas Space Grant is. Texas Space Grant is a part of the national network of space grants comprising all 50 states, Washington, D.C., and Puerto Rico, supported by the NASA Office of STEM Engagement. We are a line item in the congressional budget and recently celebrated 30 successful years in engaging and inspiring the STEM workforce. We are also supported by the Space Grant Foundation, a nonprofit that supports expansion of our programs and funding. If you go to the spacegrant.org website, you can find more information about our national efforts, as well as the Space Grant Foundation online store, which offers a wide variety of great space and STEM products, and also a link to donate to the foundation. The Texas Space Grant Consortium includes more than 40 institutions of higher education, plus nonprofit, government, and industry from all across the great state of Texas. For nearly 20 years, our Design Challenge program has connected undergraduate student teams with NASA mentors to work on projects that align with NASA's goals. Traditionally, at the end of each semester, student teams converged on Houston for an intense day or two of presentation, discussion, and celebration. Students were able to meet face-to-face with each other and to meet many NASA insiders, faculty advisors, and other professionals. This semester, as we continue to navigate the pandemic, know that TSGC stands ready to continue to inspire the next generation of the STEM workforce, with social distancing for the moment and back in person as soon as we are able. 2020 has been an extraordinary year in many respects. Before we start the student presentations, I'd like to show a couple of videos that highlight NASA's accomplishments and where we are headed in the future. The first one is titled NASA 2020, Are You Ready? So are you ready? NASA did not stop this year, and neither did our student teams. Their work on their projects will have a direct impact on NASA, as past teams have already. These students are the Artemis generation, and the next video is all about them.
"50 years ago, we went to the moon. We called it Apollo.
What many people don't know is that Apollo had a twin.
She was a woman named Artemis,
goddess of the moon.
We are returning to the moon
as a new generation of explorers.
This time to stay.
And to prepare to achieve humanity's next giant leap of sending the first human missions to Mars.
We believe our course will redefine what is possible.
That we would discover life-saving,
Earth-changing science.
And that the challenges ahead will inspire generations.
This is our manifest.
For all who wondered if we could return.
For all who dreamed of pressing beyond.
This is your calling.
We go for all of America.
We go.
We go as the Artemis generation.
We go.
The plan to return to the moon with Artemis has sparked something special in these students. In September, Texas Space Grant had more teams than ever apply for the Design Challenge program, 40 applications for the 20 spots selected. Today, we're going to hear from 10 of the teams, and our schedule is shown here. Each team has a total of 20 minutes. We'll show their 10-minute video, and then the team will have 10 minutes for question and answer time. Wednesday follows a similar schedule, preceded by our guest speaker, Mr. Monty Goforth, from the Strategic Pursuits and Partnerships Engineering Directorate at the NASA Johnson Space Center, who will speak about our path for the Artemis generation. As a preview of his talk and some final words of inspiration for our teams today, let me show one more NASA video. It's called Dreamed of This.
And as we leave the moon, we leave as we came, and God willing, as we shall return.
You probably dreamed of this.
Liftoff on Apollo 11.
You probably replayed this moment 1,000 times. You probably imagined the awe-inspiring, indescribable rush of the ride. You probably celebrated the miraculous, cheered the momentous, and mourned the shocking. You probably still dream of what could be. We did. We do. And while many thought we were through, no. We've been learning, we've been building, we've been training. And now, it's time. Because the next frontier is not just for the next generation. It's for this generation. It's for me, and it's for you. For everything we still dream about. We go as Artemis.
Okay, welcome again, everyone. If you are just tuning in, this is the Texas Space Grant Consortium's Design Challenge Showcase. I'm Tim Urban, the director of the Texas Space Grant Consortium. With me online are Talia Jurgens and Angelica Cruzinga. Our first team is scheduled to begin at 1 p.m. and our last team at 4:20. And we will strive to stay on time throughout today's showcase. That means if we do fall behind schedule, we will shorten the breaks. So audience members, this is the way you can ask questions. At the upper right-hand corner of the screen, there's a link to slido.com, slido.com. You can ask your questions there by entering the code TSGC. You can also view and upvote other people's questions. After the video, I will moderate the Q&A session by reading the top voted questions for each team to answer. And students, please remember that once you have been promoted to panelist, to keep your microphones and videos off until the video has ended. For the Q&A session, please unmute and if able, show your video so that the audience can see you as you answer the questions. After the Q&A session, team members will be returned back to attendee status in preparation for the next team. Okay, so let us begin with our first team this afternoon from the University of Houston. This is our sole returning team from last semester, and it is Mamba Mentality.
Hey, this is Team Mamba Mentality, and today we're going to be presenting our Advanced Spacecraft Lighting Control System. I'm Team Leader Eduardo Cantu, and alongside me are members Omar Beg, Saeed Jafari, and Yash Patel. Our mission for this project was to update NASA's current spacecraft lighting network system. We wanted to do this by implementing features that increase power efficiency and allow crew members to access lighting fixtures through an easy-to-use interface. We also wanted to include features that help maintain circadian cycles for all crew members, and we did this by mimicking the sun rising and the sun setting. To go over what this project contains, it includes 4 different lighting sources and a web server that can control their lighting intensity and measure color spectrum, as well as a housing enclosure with the lighting and hardware included. The main features that we wanted to go for were maintaining circadian rhythm and monitoring light degradation status. We would like easy light source expandability, and this will be done via Bluetooth, as well as allowing notifications for any possible cutoff in connection. We're now going to be going into the design portion of our project. Initially for our design, we were leaning towards FPGA development for our lighting protocol that we would use for the network. But from the figure that you can see from the right, it isn't meant to be understood without proper explanation, but it is meant to convey the complexity that came with that kind of system. So we decided to go instead with the Raspberry Pi and Arduino network to provide more concrete results and easier debugging for our COVID-related epidemic that we're in.
Hi, this is Yash. Here we have a typical deployment of the system on board a habitable module. There will be one Raspberry Pi installed, which will be the master control or the main controller on board a craft. The Raspberry Pi has a built-in Bluetooth capabilities and can connect to several different devices at the same time. Each space with a habitable module will have its own Arduino, to which several different lighting fixtures and light intensity and color sensors can be installed. The example here shows a typical deployment on board a habitable module that houses astronauts in this crew's living space and the crew rest space and a lab space. The lighting profile can be independently set in each one of the spaces as required. For example, the living and rest spaces will be specifically programmed to follow a pattern and intensity that imitates a day and a night as if they were on Earth. On the other hand, the lighting in the lab space will be adaptive, where, for example, it will be profiled to promote plant growth. These profiles can be configured using the GUI, which will be available where the Raspberry Pi is installed using a monitor, mouse, and a keyboard.
A typical system with a one-space installation consists of one Raspberry Pi, one Arduino, one Bluetooth module for the Arduino, and one or more light intensity and color sensors, light fixtures, and the MX shield. The Raspberry Pi is what the graphical user interface runs on, and it can be controlled using the monitor, mouse, and keyboard connected to it. It is capable of communicating to several different Arduino microcontrollers wirelessly using Bluetooth. The Raspberry Pi requests light sensor data from Arduino microcontrollers periodically to ensure both health and accuracy of the send commands being implemented. The Arduino microcontrollers control elements within a space. The light intensity and color sensors connected to it, and the Arduino collects data from it and passes it upstream to the Raspberry Pi when requested. It also controls the LED light fixtures connected to it within a space. It communicates with the Raspberry Pi wirelessly using Bluetooth and communicates to the sensors and light fixtures on a wired connection, specifically using a DMX shield for the light fixtures. The color spectrum sensor or the light sensor is connected to the Arduino and can read RGB color values. It can measure light intensity of up to 500 lux. The Bluetooth sensor has a Bluetooth 4.0 capability that sets up a communications bridge between the Arduino microcontrollers and the Raspberry Pi within a range up to 100 meters. The Raspberry Pi can connect to up to 8 different Bluetooth modules, which translates to the fact that there can be 8 different species controlled with one Raspberry Pi. The DMX shield is an attachment to the Arduino microcontroller, and it establishes a communications link between the microcontroller and the LED light fixtures.
So here's a visual of the Arduino setup. Going from left to right, you can see the first thing we have is a Bluetooth module, which is connected onto the breadboard. Below that, we have the DMX shield, which is responsible for the connection between the Arduino and the DMX light. And below this DMX shield is actually the physical Arduino. And then on the top right, we have our color spectrum sensor, which is responsible for sensing our light intensity and colors.
The graphical user interface is able to accept sunrise and sunset times from the circadian rhythm, measure the light intensity of the light sources, as well as monitoring the degradation of the light sources. When the user opens the GUI, they will be able to input the RF COM ports for each light as well as the circadian rhythm. When the sunrise and sunset times are set, the lights will gradually light up or dim by 25% every 15 minutes. This will continue until the light sources are all at DMX input value of 255 for lighting up or 0 for dimming down. As well as circadian rhythm, the GUI will be able to monitor the light degradation of the light sources by showing a notification on screen at less than 50 lux when not supposed to. In addition, the system is able to notify the user that the Arduino is disconnected from the Raspberry Pi through Bluetooth.
There were a few shortcomings due to the COVID-19 pandemic that's currently going on. One of them being that all of our meetings were virtual, and so not all of our primary goals were able to be accomplished. One of them being the fact that we wanted to create an enclosure for the system. At first, we thought we could accomplish this. After finding out that one of our team members actually contracted the virus, we decided it'd be best to not meet at all in a physical setting, and thus everything was put onto a virtual setting. So it was difficult to construct this enclosure because of that. Not only that, some of the secondary goals were also set back because of this, including constructing the voice command system and the plant growth system. After completing our project, we decided to do some further research to see what other implementations and ideas we can add to this lighting system. After doing some research on published patents, we saw some interesting patents that kind of pushed our own ideas into ways to expand the lighting system. This included creating a self-adjusting lighting system based on the viewing location, as in where a viewer would look at a certain area, whether it be a screen or a room, and the light would automatically adjust to the needed brightness of the person. In addition, one of the patents that we came upon was a lighting alertness system, which also could be very well used within a spacecraft for the purpose of keeping alertness within the astronauts and crew members.
So there was audio for the last slide. If anybody has any questions for us, please feel free to ask, and we'll answer the top questions provided.
All right, team, I think if you can start your video, people can see you. There you go.
I can't get my video open from my desktop computer. It's from my laptop, and I would have to rejoin. Would it be okay if I did this, or would you guys want me to rejoin?
That's fine for now. We don't need you to rejoin.
Okay.
All right, we have one question so far. So audience, please go to slido.com, enter the code TSGC, and start asking questions. One so far, where do you anticipate this would be deployed?
So ideally, it would be used for, as kind of was mentioned in the NASA videos that we showed, or that you all showed earlier, for deep space missions, especially. So once we have a base on base on the moon and going to Mars, and then hopefully to other planets, this would be most efficient and most useful. Then, especially because of the power conservation abilities, that would be very useful for deep space missions.
Yeah, ideally, we would want them to be used for spacecraft internally, because with the systems given, there's knobs and switches, and there's need for a more mainstreamed process that can make it easy for crew members to access these controls. Yeah, and also improvements towards expandability on the network. As we mentioned on our presentation, there was two systems, the Raspberry Pi and Arduino system, and work is being done towards allowing multiple lighting fixtures to be added towards the Arduino system, allowing for an entire network to be created, in turn allowing a more efficient lighting network for the spacecraft that we have right now.
Okay, we got another question here. If this project were to be continued next semester, what would your future project development plans be?
I think we would add like an Ethernet instead of working through Bluetooth. We would communicate the light with the lights through Ethernet rather than Bluetooth, because it's more stable and we could add more lighting fixtures.
And also kind of what we mentioned on the last slide about some of the patents that we had researched, some extra features that we thought could be very useful for astronauts and crew members in space would be maybe implementing something that would create alertness for crew members, say if they're working on a very specified and focused task. One patent we saw would essentially pulse lights and give like a flashing light at a certain lux rating that would help to create alertness and focus for crew members. So that's something, later on could be added as an extra feature that would be helpful possibly.
And a goal that we wanted as well was to be able to read color spectrum readings towards plant growth. Usually for that, you have to make sure that you have a good environment for that, and our system would be able to detect that as well. That was another goal, and also including voice commands. So being able to say like room 1 start circadian rhythm, and then it begins the lighting cycle for natural sleep. So basically voice command, plant life growth, expanding the network, and also an enclosure design, something that's efficient for adapting to any kind of system in terms of a spacecraft or even a room or building of that sort.
Okay, great. Next question. Going back to the beginning, I guess, what would be the purpose of the lighting system? Just for comfort or for astronaut health?
I would say that it initially was for comfort, but the added element of circadian rhythm would definitely benefit the astronaut's health on a biological aspect, due to with the sun rising and sun setting, it has an effect on our ability to focus throughout the day, and in a sense be productive. So having a system that can replicate that can increase a lot of things for crew members on board. So in a sense, it would be doing both. But what we want is to create a more effective lighting system that doesn't require so much user input, and instead provides them an easily accessible, so in our case, a GUI to control the entire system instead of relying on knobs and switches, while also providing them alerts on the health of the system and showing them like, hey, light 3 is currently off. There needs to be an update in that, compared to now where there's not really a way for astronauts to know the health system of the light connected to the network.
Okay, next question. What type of database system are you using to store the data logging?
We're just we're not using any database system. The Raspberry Pi was just written in Python, so we just kept everything in like lists.
Okay.
So,
That would probably be an additional thing that we would work on if we were to continue this project further. It would be establishing that database.
I think this like so far this project would be more, it's like more bare bones than it should be. I think if we continued it, we can make it more efficient using databases.
Okay, next question. Were there any specific goals for the energy efficiency of the system? For example, any power consumption advantages over current systems?
There was, for maintaining a certain light intensity value, we wanted to keep a reading of 500 lux for the lighting fixtures. And you don't want the fixture itself to be outputting at 100%. You want it to be at around that intensity. So a program within our code that adjusts for the lighting system to stay at that intensity can provide a power efficiency medium for the system to ensure it's not taking up more than is required. And the same goes for those earlier circadian rhythms that were mentioned. Those are automatic cycles that help to ensure that certain lights don't stay on longer than they have to be.
Okay. And getting more into the settings now, next question is, how are you creating routines for the circadian rhythm and setting the sun positions?
We didn't set any sun positions. It just sets a time for the sunrise and then the time for the sunset. So once the sunrise time arrives, then we'll just start incrementing the light every 15 minutes, or when sunset comes, we'll just start decrementing the light every 15 minutes to just mimic the like sunrise and sunset.
Okay, good. I don't see any more right now. Let me ask, so what is the TRL, the technology readiness level of your components right now?
Close to between level 4, level 5. It's in very early stages. There's still some implementation needed with components that could potentially be used on board spacecraft as well. These are not radiation tolerant components, and we're not sure if NASA will require them to be, so it's not at the deployment level just yet.
Okay, thank you. Thank you. Any last minute questions from the audience? Oh, what is DMX?
So DMX is a lighting protocol that allows our system to control multiple lights through one serial connection. What DMX allows us to do in a sense is if you have one light connected to another via daisy chaining, our system is allowed to access each individual light via, I believe it's 7-bit addressing. And then once you address that specific lighting source, you can then change its values directly from there. So DMX, in a sense, is a protocol that allows us to control multiple lighting fixtures from just one single master source.
Okay, oh, we got another question here. How are you maintaining the color degradation?
We didn't get a chance to get into that for the project. We were working on it, but we managed to not finish it.
Could you explain what the color degradation is?
The color spectrum sensor would essentially just read it reads color values like RGB color values, and it would essentially output that data through serial port on the Arduino, and it would tell the Raspberry Pi what the color values are, and that's essentially where we got so far. We didn't have any response to what would happen with the color degradation.
Yeah, there were issues in troubleshooting with one of the sensors that we had in terms of the color outputs that we were receiving, and we were really focused on trying to get the lux values to read properly in a sense. With more time in the project, that implementation would have been applied, but that was one of our main setbacks that we had, including the enclosure.
Okay, well, thank you, team, very much for your time and your project. I know it's the end of 2 long semesters, not what you expected with COVID, but
right.
You persevered. Very good job. Thank you.
Thank you.
Thank you very much for having us.
Thank you.
All right, our next team comes from the University of Texas at Tyler, and it is the HEC Houston Engineering Center, Team 28.
Thank you for joining us. Our team is HEC 28, and our entry into the TSGC Design Challenge for Fall 2020 is an integrated PEM fuel cell system. Our team consists of myself, Jeff Eglinton, Robert Ma, Oscar Palencia, Marco Ponce, and Sherwan Rizal. Our presentation will follow this outline, beginning with some background into our topic, followed by our primary components, then our design and its individual components, and finishing with a conclusion. The purpose of our project is to design a simulation and to model the balance of plant for a regenerative fuel cell system that can serve as a backup energy source in a lunar environment. This slide shows a generalized diagram of how a regenerative fuel cell system works, where the fuel cell combines hydrogen and oxygen into product water, and then the electrolyzer divides that water back into gases in an ever-repeating loop. Our design objective is the BOP, an engineering term which refers to all the various supporting components and auxiliary subsystems of a power plant that are required to deliver the energy, except the generating unit itself, which in this case is the fuel cell. Our primary objective is to design this BOP in a way that it can deliver 100-watt net power while minimizing overall mass and volume so that it can be effectively delivered to the moon. We will create a complete set of models for the regenerative fuel cell system under lunar operating conditions and simulate the operation for the balance of plant. Now Robert will discuss the fuel cell and electrolyzer.
Thank you, Jeff. So what are fuel cells? Fuel cells are like batteries, but what makes them different is that they can continuously run as long as hydrogen and oxygen is supplied. The fuel cell we are using is an Infinity brand fuel cell with initial operating conditions of 338 Kelvin at steady state. It operates at nighttime for a 12-hour cycle. We want a net power of 100 watts for the entire system, but the power output of our fuel cell is 170 watts. This is because we need to account for the power uses of the other components of our balance of plant. Next slide, please. A fuel cell produces electricity through a chemical reaction between hydrogen and water. This reaction is a half reaction. As you can see in the video, oxygen enters the fuel cell through the cathode side, while hydrogen enters through the anode side. The reactant byproducts are water and heat. Next slide, please. What is an electrolyzer? An electrolyzer is a device that performs electrolysis. This process uses electricity to break water into hydrogen and oxygen. The electrolyzer fully operates during the day for a 12-hour cycle. The 132-watt usage is powered by the photovoltaic or PV solar panels. And the electrolyzer we are using is by Sustainable Innovations, and it has initial operating conditions of 323 degrees Kelvin at steady state. Inside the electrolyzer, hydrogen and oxygen is controlled at 1,379 kilopascals. It should be noted that when the electrolyzer and fuel cell are not operating at full capacity, they are not completely turned off. They remain running outside of the 12-hour cycle to prevent liquids from freezing. An example of this operating condition is running water to prevent your pipes from cracking during the cold weather. Marco will now talk about our design schematic for the balance tank.
Thank you, Robert. The following schematic illustrates our BOP design. During nighttime, fuel cell is in operation with both the reactants hydrogen and oxygen generate power through an electrochemical reaction. The gases leave the storage tanks and are heated through heat exchangers to reach an ideal temperature for the reaction within the fuel cell. The product of the half reaction is H2O. The water produced is stored in a water storage tank. During daylight, the water is fed by a pump into the electrolyzer to produce oxygen and hydrogen gas. This is also known as a recharging phase for the fuel cell. After electrolysis, both gases are passed through a dehumidifier to remove any moisture from the gases. The gases are then compressed by compressors and stored in tanks to repeat the cycle. In conjunction with the BOP design, electronically controlled solenoid valves are used to control mass flow, and the cooling system of DI water, similar to the water management system, is integrated to the BOP to keep the fuel cell and electrolyzer operational temperature within range. The lines connecting the components consist of insulated 3/16 stainless steel with an ID of 3/8 and an OD of 1/2 inch. We will now talk about the key components in our BOP. Next slide, please. Here we have our water storage tank. It is able to hold water in vapor and liquid form. Filtered water vapor enters the tank from the fuel cell as vapor and leaves to the electrolyzer in liquid form. Next slide, please. The pump in our BOP design transfers the water from the storage tank to the cathode side of the electrolyzer. Apart from transporting water, the pump increases water pressure before entry into the electrolyzer. Oscar will now talk about the gas compressors.
So once the gases leave the electrolyzer and pass through the dehumidifier, they come to the compressor to be pressurized, as shown as the values in the pressure in and pressure out. The temperature will rise as the gas compresses. Next slide, please. Now we will talk about the storage facilities. First is the hydrogen tank. The storage pressure will be at 1.24 megapascals, and the tank capacity will be at 105 liters. Next slide, please. Second will be the oxygen tank. The storage pressure for this tank will be at 1.92 megapascals, and the capacity will be at 34 liters. The oxygen gas feeds into the cathode side of the fuel side. Next slide, please. Now, these are two smaller key components that we have, which are very important for our design. One is a heat exchanger, and the other one is a dehumidifier. The heat exchanger transfers the thermal energy between the coolant and the reactants. And this is placed after the oxygen and hydrogen tanks. The dehumidifier is before they reach their tanks, storage tanks, and what they do is prevent the condensation and icing on the fuel cell and the coolant. Now I will pass it down to my member, Chuan.
Thank you, Oscar. After the research and analysis, we came up with the final design, which addresses all the thermal fluid components essential to run the system with optimal efficiency. This design minimized the risks of fuel cell from overheating and icing in the different components of the system in the long hour of operation. Next slide, please. We'd like to thank Dr. Risby for advising us through this project, Dr. Garcia, Dr. Biswas for mentoring us, Mr. Benjamin, and Ms. Jargons, and Dr. Arpon for the opportunity. Thank you everyone for your time, and we look forward for your
Okay. Good job, Team HEC 28. I think everybody is here. Excellent. So audience, Please ask your questions on slido.com. Enter the code TSGC. So just as a ballpark, can you give us an idea of the mass and volume you're looking at?
At the moment, we're still mostly in the component selection phase. We're still trying to narrow everything down exactly what we need. As soon as we have a general understanding, we should be able to provide a general mass and volume for the system. At the moment, like I said, we're still in the selection component selection.
Okay, still trying to just find the lowest mass.
Exactly.
You can get. Okay. So these all been tested on Earth, I guess. Have any been tested in space?
No, sir, I didn't have a chance to go to space yet.
Any of the components?
Currently, we're sourcing commercially available. As long as the components specifications meet basically the general requirements for space, then they can be used. If not, then we'll rule them out altogether.
We plan on testing it using Earth-based conditions, as you said, at our campus laboratory.
Okay, and then how is the lunar environment going to be different from your tests on Earth?
For example, the lunar conditions, it has a cycle of 354 hours for the day and night over the course of 29.5 days. So we have to account for that timing, and then we have to account for the difference in temperature. And our application is for inside of a lunar lander, which will be at the equator.
Okay, you're looking at the equator, not the South Pole?
Initially, it was at the South Pole, but I believe that through our mentoring meeting, we changed it to the equator.
All right, we've got some questions here now. So how large does your solar array have to be to provide the electrolysis power?
Actually, most of our design focuses on the balance of plant for the actual system itself. We know about how much power it will require to run the electrolysis. As far as the actual design of the solar arrays, that's a little bit outside of our scope.
Okay, so next question is, what was your biggest challenge?
Our biggest challenge was it was definitely working virtually. When we met in person, it was only one day out of this whole semester, and I can definitely say that it's easier to accomplish things in person compared to virtually. As the previous team stated, they had to work virtually, and it kind of slowed us down. But I would say that's the biggest issue, was not being able to work in person together.
Any other thoughts on that?
In terms of designing, I would say our biggest challenge was the calculations, because we had to calculate, the pressure and temperature for each component. And it was a lot of thermodynamics, which is, one of our hardest subjects in our courses. So it was definitely the calculation part, and trying to, use these calculations to verify what kind of parts we would need.
Okay, good. This one has 3 upvotes now. So why was the location shifted from the South Pole to the equator?
I believe that was through recommendations from our mentor, but I'm not entirely sure what the exact reasoning behind that was.
Okay. Any lessons learned from working in a team?
I actually worked with Shawan Rizal and Jeff Eglinton before in previous projects, and it was the first time with Oscar and Marco. And I could say that, I think working in teams really benefits for future professional settings because, you never know who you can get. You might not know your team members ahead of time. So, you can focus on working together for one goal and setting your differences aside to meet that goal. And I think that's a good part of this project and teamwork.
Very good. All right, another question here. Will using water pose a problem with its expansion and contraction?
Yes, that could absolutely pose a problem. As Robert was discussing, most of the challenges come in the thermodynamics, and most of our design is going to essentially revolve around keeping things at a temperature to keep water from freezing or the systems from overheating. So it's a thermal balance issue is where most of the design comes in. Most of our solutions become from insulation and keeping things from freezing in the first place. Unfortunately, the way fuel cells work is if there is icing in the membranes, the fuel cell basically becomes damaged beyond repair. So it's critical to keep that from happening in the first place.
Okay, next question. If you electrolyze the water, that takes more power than the fuel cell produces, doesn't it?
Yes, I'm not sure if we made it clear enough, but during the daytime, the photovoltaic cells are actually what run the electrolyzer. The fuel cell, it will run during the night when the sun is not available for producing power for the electrolyzer.
Okay. So maybe that was a consideration in looking at the day-night cycle moving to the equator.
Yes.
So how would things change if you moved to Mars?
I really thought about that.
Probably we have to run design for the long hour run and also consider for the temperature.
Okay. Next question. Any plans to make a state space model to represent your whole system? And if so, do you plan to implement any controllers?
Eventually, we hope to have some sort of power management system that will run basically everything. It'll be an integrated system. Unfortunately, none of us are electrical engineers, so we'll probably have to have a little help on that aspect. We're all mechanical. But yes, eventually some sort of power management system will run all of the electronic valves, which will regulate mass flow, determine if something is causing too much of a parasitic load. All of those factors will be run by a centralized power control unit.
Okay, next question. Is corrosion a concern at all for your project?
To some extent, yes. Oxidation is always a concern. Fortunately, our system is almost entirely closed loop. So that should minimize, and it's basically always moving. So eventually, yes, the corrosion would be a long-term problem. At the moment, we're running in short. 100 watts isn't very much, so it's not running that long.
Okay, and last question here. What is the benefit of a hydrogen fuel cell over something such as a small nuclear reactor?
The first thing is the most efficient one. We have a higher efficiency with a hydrogen fuel cell. And then it can run continuously for long hours as long as the fuel is supplied, and then we have like no other emissions except the water. So it's better than other.
I think by not using a small nuclear reactor, of course, a nuclear reactor, if anything happens like a disaster, could probably give out radiation as opposed to a fuel cell.
Yeah, like Marco was saying, there's a lot less risk involved in using hydrogen, oxygen, and water as a fuel source.
Okay, thank you very much, team. Welcome to the Design Challenge, and good luck next semester.
Thank you.
Thank you.
Thank you, Dr.
Thank you. Thank you.
Thank you for the questions.
Okay, our next team is going to be the University of North Texas, Denton Space Eagles. And audience, go ahead and use that slido.com to submit your questions. You can start submitting them as soon as the video starts and you have something to ask.
Hello, and welcome to my team's presentation. Today we are talking about our private cloud with IoT Design Challenge. We are Team Denton Space Eagles. Because we can't be in person, we will introduce ourselves so voices aren't confused. I'm the team lead, Mark Yonker.
Hi, I'm Shanda Lee.
Hi, I'm Micah Warren.
Hi, I'm Yichen Fane.
Hi, my name is Ricardo Garza. To introduce this project, I want to give you some background. In these last couple of years, NASA has had an increased demand for monitoring and producing data. The reason being space communication, vehicle health, experimental data, and engineering data. That being said, the amount of data being produced would increase in next years because one of NASA's goals is to return to the moon. And to help achieve this, NASA plans to seek out the use of IoTs, or the Internet of Things, which have become widely popular in the last couple of years. This should help reduce the time needed to process all data from experiments and other areas. Currently, data is sent to Earth to be processed, but that data transmission is bottlenecked because of the connection. This gives the transmission a high propagation time. The objective for this project is to examine an open source IoT cloud platform, which will have a couple test applications to demonstrate its capabilities, and still have the data stored and processed on board, while only sending relevant data back down to Earth. The way it was designed is to have 4 applications. These 4 applications will send their data up to the cloud, have the data processed, and in some cases, have the data sent back down, like on a motion sensor camera, and it would have it displayed on the LCD.
For implementation, our project will have 4 different applications to evaluate cloud capacities, which are field monitor, health monitor, weather station, and motion sensor camera. These 4 applications are built to stress the server to show off their features and the server's capacities. The field monitor monitors real-time air pressure, temperature, and the fuel level inside the fuel tank. It has an alert for dangerous fuel status, like high air pressure, high temperature, or running out of fuel. In addition, it can calculate the remaining flight time and distance according to the fuel burning rate and the speed of the spacecraft.
The purpose of this application is to test the IoT platform by acting as a monitoring system for astronaut health. It is built using a Raspberry Pi 4 with an oximeter sensor, a pulse sensor, 2 microphones, and 2 speakers. It will be served as an assistant for monitoring astronaut health status, such as blood oxygen level and heart rate. An alert will show on the cloud side if abnormal data present to inform scientists of critical condition. Also, in case of emergency, speakers and microphones will be used for communication between the astronaut and the cloud site.
And the third test application is going to be a weather station. It has an anemometer, a wind vane, and a rain gauge for measuring the amount of rainfall, the wind speed, and the direction. It has a temperature, humidity, and pressure sensor for reading the current climate. And for example, let's say you have high winds, it can send out an alert to the cloud or the IoT platform and say a high wind advisory.
Our fourth application will be a motion sensor camera. Motion sensing has a wide range of uses, from automatic doors to floodlights outside your house. We've decided to use it to record any motion detected by a PIR sensor and ultrasonic sensor. Using both in tandem increases accuracy and gives extra data like the distance the object was at. When motion is sensed, the camera is activated and will record and then upload the footage to the cloud. In the cloud, recorded footage will be run through machine learning algorithms using Image AI and perform object detection on the video. Image AI is an open-source Python library with self-contained deep learning capabilities. Once processed, the video will be displayed in the cloud and sent back to the edge to be displayed there as well.
For the IoT cloud platform, we have chosen to use ThingsBoard as the foundation. The platform will act as a gateway for devices to connect to, regardless of the communication protocol, and for users to view and control the devices connected. Some of the communication protocols that ThingsBoard already supports and has community examples of are MQTT, HTTP, and Bluetooth Low Energy. But these are just a few examples of what is supported, and it also has support to add other communication protocols. The platform also has the capabilities to raise alarms if a device's sensor data meets a predefined condition. This alarm can trigger a multitude of different actions by the platform to happen. For example, having the dashboard updated to show the active alarm, have the platform send a message to another device so it can handle the alert, and many other things. While ThingsBoard has dashboards to visualize data already available as part of the platform, we would like to explore the idea of having ThingsBoard connect to an external dashboard program, like NASA's own open source dashboard, OpenMCT, to visualize data. This semester, we have made some general progress on the test applications and gotten ThingsBoard installed and set up. In our demonstration setup, we have a virtual device that is reporting temperature data to the server utilizing the HTTP protocol. The server then records the data, processes it, and displays it in our demonstration dashboard that is set up to show data in real time with a current reading and a history graph. The current dashboard is just a basic representation of what ThingsBoard dashboards can do. It has the ability to rearrange the graphs in any manner that the user wants, have more complex data visualizations, and have many different telemetry sources. We're planning on finishing the 4 separate test applications that will connect to the cloud, and then we will integrate those data streams from the test applications into that cloud, and then design dashboards and alarms around that data. We will then display that data on the dashboards.
The whole project is planned to be finished by the end of next semester. Right now, we are in the state of syncing up sensors of each test applications and setting up the raw connection between test applications and the cloud. As the preliminary results shown, the features of the IoT platform we chose are very powerful. We're planning to connect test applications to the cloud by end of this semester, and we are very excited to continue working on the project and further expand its functionalities. We would like to thank everyone on this list for helping us on the project and helping coordinate this event. Thank you very much. Here are the references that we used. Thank you for watching.
Hello.
Okay, thank you for your video. And we have everyone online, I believe.
Yes.
Yes.
All right. So audience, please submit questions through the Slido app, slido.com, enter the code TSGC. First question, what location or environment do you plan for placing your sensors?
Which specific application? Because we have 4 different ones that we have.
Right, I guess go through all 4 and maybe describe how you came up with those 4 and where you would place them.
See, for the weather station, I know you can pretty much put it anywhere outside in most environments. Whoa, I'm echoing. And then the way I have it planned out was to be able to anchor it down somewhere. I'm still looking at ways to put it down somewhere so you can put it down and then it can just send data up to the cloud.
For the motion sensor camera, it would have to be inside, but it could be outward facing through some kind of window, and it would, or even be used for interior reasons. But it, especially in a space environment like the moon or in a station, it's not built to last in that kind of environment currently.
Yeah, and for my health monitor, I'm going to put on the glove and can wear it. Yeah.
Yeah. So for the field monitor, can you hear me?
Yes.
Yeah. For the field monitor, definitely sensor will be placed inside the fuel tank, and they will be connected to a Raspberry Pi with a LCD to show the data of the fuel. Yeah, that's it.
Okay.
That was all 4.
Great. Next question. How does the system deal with wireless dropouts?
We can set up the system in such a manner that the applications themselves send a timestamp, so that way there's not a miscommunication of when the data was sent. And then if the application does connect and it's a more critical application, then you can have the IoT platforms make a sound, send an email, do some sort of custom alert.
Okay, next question. How does this system compare with current systems?
Well, with this system, it is trying to think of a good current system that is available. Like if you're thinking more of the Google Home or Siri, Internet of Things world, this is definitely more open to be coded, as you can use basically whatever type of communication protocol you want. So you're not limited to what other developers have already done. You can develop something yourself more easily and the functionality that you want it to do.
Okay. Next question here. How does the system decide what is important data that it sends to Earth and regular data that stays on board?
Like
this will all be set up
by a scientist or who just some admin position that is going to decide what is pertinent, what is worth taking up bandwidth and time. So it's going to mostly be user defined, but if they want to have a smaller intervals of sending specific data, or if they only care about if a disconnect happens, or then they can just define it the way that they wish.
Okay. All right, no more questions right now. Let me ask, where do you envision this being deployed eventually?
It can be deployed on the moon base that's planned. It can be deployed even on way in the future on a Mars base. It's private cloud, so it can be moved to wherever it is needed. Really, it doesn't really rely on any outside sources other than power.
You know, we're designing it in such a way that it just runs off of a normal computer and uses Wi-Fi or Ethernet.
Okay, and so next semester you're working on a GUI, correct?
Yes.
So what do you envision?
Working with the Things board dashboards and hopefully integrating that as well with that NASA OpenMCT, which is another dashboard program.
Okay, what do you envision your alerts and alarms to look like?
For more, maybe less serious type of alarms, it could be as simple as an email. And if it's something like a bad fuel status or just adverse weather, it could be something like an audible alarm through speakers or whatever is available.
Like a light LED and speakers to really get the attention of everybody on board.
All right, very good. Does our audience have any more questions? Slido.com. So how did you find working as a team socially distanced?
Well, we're lucky enough to where we have been able to meet in person, social distance, you know, but most of the time we do meet online, usually in Discord, and we just do weekly, bi-weekly meetings, just making sure we're caught up on everything. And we just received our parts today, and we'll be getting them and working and putting our sensors together real soon.
Excellent. So your lab is open right now?
Yes. Our professor, Dr. Robin, he's very careful about everybody, making sure that we're all far enough apart and that COVID doesn't affect the situation as much as possible.
He will not start class if we are sitting too close together.
Nope.
That's true.
Very good. All right. Well, thank you and good luck next semester.
Thank you so much.
Thank you so much.
Thank you.
Okay, so that concludes our first session. We're going to take a 10-minute break and we will be back at 2:10 for the next session. Welcome back, everyone, to session 2 of the Texas Space Grant Consortium's Design Challenge Showcase. Session 2 has 4 teams starting at 2:10, and session 3 will have 3 more teams at 3:40. First up for session 2, we have the team from Texas A&M University Kingsville, and it is Tamuk's Team 6. Audience, please go to slido.com to submit your questions, and again, use code TSGC.
Hello everyone, this is Tamu Team 6's NASA TSGC Design Challenge presentation of our origami folding solar array project. This is the team's first semester conducting the project. Today, we will start the presentation with an introduction of the team, followed by the project background, scope, design requirements and constraints, and design considerations. We will then finish the presentation with the group's next steps and conclusion.
Hello, my name is Ricardo Cuellar. I am a senior mechanical engineering student.
Hello, my name is Leslie Carrion and I am a senior mechanical engineering student.
Hello, my name is Aaron Rocha and I'm a senior mechanical engineering student.
Hi, my name is Jonah Cross and I'm a senior mechanical engineering student.
Hello, my name is Mauricio Fernandez and I am a senior mechanical engineering student.
Hi, my name is David Balderas and I am a senior mechanical engineering student. We all attend Texas A&M University Kingsville. We will begin this presentation with some background on the project. A solar array is an assembly of solar panels used to facilitate the conversion of sunlight into electricity. Solar arrays are often used on space vehicles since there is no other easily accessible power source in space besides sunlight. Origami is a traditional Japanese paper folding technique most commonly known for creating intricate moving designs. Recently, this paper folding technique has found its way into many engineering applications, including robotics, medical devices, policing equipment, and much more. This is because origami offers a great deal of unique advantages to your engineered design, specifically the ability to collapse large structures into compact volumes. One application that sees significant potential for the implementation of origami engineering is the use of large space solar arrays. As the importance of space exploration increases, larger and more powerful spacecraft will be required for longer space missions, which will in turn require a large solar array to meet these power requirements. This can be an issue if the expanded surface area of the solar array is significantly larger than the size of current-day launch vehicles, because then the solar array will not be able to fit inside the payload bay. Our proposal is to design and prototype a solar array for a large spacecraft that uses origami folding techniques to help retract the structure into a compact volume that fits inside the payload bay of a commercially available rocket. A few of the performance indicators to help gauge the success of our design will be the solar array's packing factor and overall weight. We must design a solar array with a large expanded diameter to retracted diameter ratio and a large expanded surface area to packed volume ratio, while ensuring the complexity of the design does not significantly add to the weight. This will help determine the effectiveness of the use of origami folding techniques compared to other less complicated retraction and expansion methods. Aspects not included in the scope of this project will be the implementation of a solar tracking mechanism and the electrical engineering concepts involved with the electronics and wiring of the solar panels.
Hi, my name is Jonah Cross and I'll be discussing design requirements for the origami solar panel. The expected lifespan is 30 years with an energy output of 150 kilowatts. Due to the extreme conditions in space, our solar array will need to be immune to ultraviolet rays, or UV, and atomic oxygen, or AO. It will also need to withstand impacts from micrometeors and the plasma field, as well as temperature cycling that ranges from negative 250 degrees Fahrenheit to 250 degrees Fahrenheit. Our goal is to have the solar array weigh less than 4,800 pounds. When folded, the solar array will need to fit into the payload area of the SpaceX Falcon with a diameter of 17 feet and a height of 43 feet.
We are considering 2 different folding patterns for our design. The first is the accordion folding pattern that is currently used on the ISS. The advantage for this one is that that it is less likely for damage to occur during transport and deployment. And the other one is the flasher folding pattern that we are leaning towards because it has about 10 times increase of deployable diameter to folded diameter. And by adding fold lines along other axles, we expect to maximize the stored volume space within the transport vehicle.
On the left, we have an example of the hexagonal flasher model being expanded and retracted, and on the right side, we have a square flasher design model being expanded and retracted.
For our mathematical model, we will be using a Mathematica 12 notebook that sets up the constraints for a general flasher and solves for the vertical coordinates for both the crease pattern and the folded form, the total surface area, and the folded volume. So for the inputs, M is the number of sides in the central polygon the pattern will wrap around, and you can see that on the top right picture. H is the number of axial bends between the bottom and the top of the folded cylinder. You can see that at the bottom right picture. Capital H is the height of the packed membrane, and we find this with the formula H is equal to lowercase h over square root of 3L, with L being the side length of the polygon the member folds into. R is the number of rings in the pattern that you can see on the bottom left picture, and delta is the specified spacing between vertices.
On the left is a CAD model of a segment of a flasher origami fold, and on the right is a CAD model showing a conceptual folding of this origami fold.
I'll be going over the kinematic structure and how these two self-deploy methods, the motor-driven truss method and the scissor method work. So the motor-driven truss method, this method uses springs and a motorized truss to deploy the array open. At its initial state, the springs are then released, causing deflection to self-open the array, then having the motor fully unravel the array. As goes for the scissor method uses a shape memory polymer and rotational pins and rotational hub to operate.
After considering other actuators used in similar projects, we have decided to move forward with an electrically powered actuator. Once we determine the kinematic structure for the solar array, we can determine if this electrically powered actuator should be a motor or a linear actuator. Here on the slide are some pros and cons for a motor actuator.
The thickness of the solar panels used in this folding mechanism is very important because the thickness will impact the solar array's ability to fold into a compact structure, and it will also determine the gap that is needed between the panels so that way the mechanism can fold properly. The overall thickness of the solar panel is determined by the panel substrate, the solar cells, the glass, the encapsulant, along with the other layers that make up the solar panels themselves. After contacting SpectroLab, we found out that the substrate is completely customizable and can be customer defined, so that way it meets the desired design specifications. Pumpkin Space Systems told us the same thing, however they were able to provide a general thickness for each of the layers that make up a solar panel. An overall solar panel thickness will be established after discussing our project further with the solar panel manufacturer. As to the solar cells, we're considering 3 of SpectroLab solar cells. However, we would more than likely use the XTJ since it has a higher efficiency and higher power output.
Origami is usually performed on paper, which is considered a zero thickness model, but our structure has a finite thickness. We have compiled our top 3 options when it comes to thickness accommodation methods for folding. The first method, the offset panel method, utilizes the zero thickness plane and is kinematically equivalent to the original origami pattern. This means that the offset panel design folds in the same plane as the zero thickness model would. The downside to this method is that there are high stresses on the joints due to the offset distance. Next, the double hinge method allows for great movement throughout the entirety of the folding process. On the other hand, the panels need to be shaved down around the edges to prevent interference from folding and unfolding. Finally, the membrane method was the most common method found in the literature. It requires a thin flexible membrane under the solar panels to serve as the flexible joints for the array. This method has excellent flexibility, but constant tension at the edges of the structure is needed to keep it in the deployed state. Also, this method does not guarantee consistent motion, which has to be taken into consideration when a deployment method is selected. In the next slide, there are some animations that we created to simulate the motion of each thickness accommodation method.
Our next steps include finalizing and establishing external loads and other constraints. We will also establish the thickness accommodation technique that we will use for our mechanism. We will determine the solar panel thickness and begin a mathematical model for the designs that are being considered. From those results, we will be able to perform a down selection of the folding patterns and decide which one is the best for our application. From there, we will choose our actuator and deployment mechanism that best suits our design. Then we will finally initiate a CAD model and analysis, and then begin our scaled prototype.
Okay, team. If you are on, go ahead and turn on your camera, unmute yourselves, and we have some questions for you. So the first question is, did you find the design limited by the complexity of folds? It seems that folding techniques will be limited by the mechanics of the design. Was this true?
Yes, sir. So that's why we started looking into a flasher design. A lot of the designs were limited just because of the thickness. But through our research, we found that the flasher design was the best use for this project.
Okay, and then I think there's a follow-up. It says, furthermore, was the folding technique limited by the solar panel material? They seem like they would be delicate, limiting how compact you can get them.
Yes, sir. So for the material, I guess, yeah, we're looking into that right now, and that's some of the stuff we do have to take into account, because depending on the thickness and the material and everything is how much the vertical spacing we're gonna have to give it so it doesn't get damaged.
And was that referring to the solar panel materials?
Correct. I think because you had mentioned paper was essentially a zero thickness material. How thick are you talking about?
Some of the literature we read had like a cross-sectional picture of a current, or not current, but a solar panel design that they were planning on sending to Mars. It was just like a research that they were doing. Some of the materials that they had were in terms of micrometers, so they were really thin materials. Some of the solar panels they had were micrometers thick. The epoxy that was necessary to put the panels on the folding, well, it's a thin membrane that they used. They used the membrane method out of the methods that we spoke. So yeah, the panels were really thin in terms of micrometers, and as well as the epoxy and the membrane themselves, they were all very, very thin.
Okay. Next question. What are the advantages of using Mathematica for folding analysis? Do you feel that the model accounted for materials and thicknesses adequately?
Yes, sir. So our main reason for choosing Mathematica was when we were reading some dissertations by other people, there was already a whole notebook to solve for everything. So we really didn't have to like go into exploring the new, like all new equations and doing it by hand. Everything was already there. Like we stated on our slide, we just had to input some of our design factors, and then we would get everything we needed. So that was our biggest factor for using Mathematica.
Okay, good. Next question. Do you think finite hinges, such as the ones demonstrated, would be easily damaged in the areas it will be placed?
So that's going to be dependent on what method we use. For example, the offset panel method, one of the downsides to that method was that it would experience more stress in that offset distance. So we're still exploring the different methods a little bit more, but we're more leaning towards the membrane method. That is because in the literature that we've read, that method has been most widely used. So out of all of the methods that were explored, that method was most commonly used in previous designs. So that method would use a thin membrane that the panels would be kind of just glued onto, with the use of an epoxy. So that one wouldn't really experience too much stress in the actual the stress would be experienced in that membrane, that it's going to be the panels are going to be a certain distance away from each other to accommodate for the thickness. So for example, if there's a valley fold, so those folds would kind of go, this is a mountain fold, the valley fold would kind of go the other way. The panels would be like this and go like that. Each fold has its own amount of thickness that is required to fold the panels without damaging them. So for example, the valley fold would require a 2 times thickness, while the mountain fold would require a 1 time thickness as a gap between the panels. So that will kind of prevent the panels from damaging each other. In terms of the other methods, we still need to kind of take a look into how exactly they hinge per se.
Okay. All right, audience, go ahead and ask some more questions on slido.com. In the meantime, let me ask, you said you were going with an electric actuator. Why did you choose that over the memory polymer?
We chose the motor because we were more familiar with it. It had a lot more pros that we related to. It was very easily to assemble, and the thermal actuation was very difficult to put in. We didn't find too much research for it. So we're just trying to go with the easier route and pick a motor.
Yeah, and on the thermal actuator, we kind of noticed the designs and literature that we're using the thermal actuators. Those, or the shape memory polymers, those seem to be more conceptual designs. We weren't able to find a lot of material where they were actually implemented into space. So we're kind of taking that as, okay, well, if we go with the electrically powered actuator, we'll have that, it's probably used more often for a reason. So we'll have more resources to go that route as far as, or in comparison to the shape memory polymer.
Okay, we have one more question here. What material would the epoxy be made of for the membrane?
So that we're gonna have to explore a little bit further. Based on one of the literatures that was read, they did mention the use of DuPont, or that they mentioned that brand. So we were planning on taking a look into their selection of epoxies, as well as material for membranes that they would have available. So as of right now, we haven't necessarily explored too much into the epoxy. So we'll probably take a look into that in the future to hopefully have that answer ready for the next presentation. So sorry about that.
Oh, that's great. Thank you, team. Good luck next semester, and good luck on your project.
Thank you.
Yeah. Thank you.
Okay, our next team up is from the University of Texas at Austin. Again, team members, remember, keep your video and audio off as you're being promoted to panelist during your video, and then turn them on after your video so you can answer questions. Audience, you can begin submitting questions as soon as the video starts at slido.com. Use the code TSGC, and you can look at and upvote other people's questions as well. So team number 2 in session 2 is from the University of Texas at Austin. They are the NASA Mount team.
This is the final presentation for the design of an antenna mounting structure for zero-gravity crewed environments by Team NASA Mount, Sharif Chang, Zachary Keller, Jesse Reisner, and Claire Soroki. This project seeks to design an antenna mounting structure for space applications. The mounting structure often dominates any antenna installation in size, weight, cost, and schedule. The mounting structure also places the antenna at the most optimal position to avoid radio opaque structures and provide good signal range. The antenna mounting structure must also withstand astronaut kick loads and other environmental factors. Additionally, deployability in such a structure is often desired for applications where space is heavily constrained.
So the project background applications, the antenna mount system we are designing will be used to deliver Wi-Fi to devices outside of spacecrafts. The two main applications of our design include number one, the retrofit design for the International Space Station, and number two, a new design for the future Lunar Gateway missions. So for the first application, the International Space Station, this will be a retrofit design to the already existing antenna mount. The antenna must attach to a pre-existing handrail, and the handrails must not deform from the kick loads from the astronauts. The second application is the Lunar Gateway missions that's set to start in 2024. There are no pre-existing attachment constraints, and the antenna structure will be attached to rigid beams. There is a possibility to explore deployable designs. However, many mission details are still classified.
Our problem statement is stated as such. The objective of this project is to propose multiple novel concepts for antenna mounting structures in a zero gravity environment, quantify their performance using simulations, then choose the optimal design to prototype and test.
Our team developed a set of engineering requirements to help evaluate our designs. The most basic of these requirements are the physical constraints, which include the weight and antenna height of the structure. Additionally, each design must also withstand the kick loads, and these kick loads must not exert enough torque on the attachment point, whether that is the handrail or the external rails of the Lunar Gateway mission. Additionally, the designs must also function in space applications, which include being able to function in a vacuum, being able to withstand extreme temperatures and vibrations from the spacecraft. Finally, the designs must not injure astronauts in any way, either from snapping back or from any sharp features which may damage the astronaut spacesuit. 3 leading concepts were developed in order to explore different applications. One design was dedicated for the International Space Station, while the other 2 were dedicated for the Lunar Gateway mission. Additionally, one of the concept variants is deployable, while the other 2 are pre-deployed designs. Our team also explored different design aspects such as the attachment point, some having single point attachment and one design having multi-point attachment. And as the designs are meant for different applications, 2 of the designs will explore a rigid design structure, while one of them will explore a compliant design structure. Concept variant 1 is shown here, which is attached to the handrail of the ISS. Concept variant 1 consists of a lattice structure, which is meant to both reduce the overall weight of the structure and increase the compliance in order to absorb the kick loads and prevent the handrail from deforming. This design is advantageous for its lightweight, but its compliance could also be disadvantageous if it snaps back and injures astronauts, and the compliance could also be an issue due to vibrations from the spacecraft.
Concept variant 2 is seen here and is a rigid multi-point attachment that connects to the Lunar Gateway. It uses an I-beam to minimize weight while increasing the strength in its weakest direction. Some advantages it has is it offers rigidity due to its multiple attachment points and can also act as a handrail for astronauts to grab onto during spacewalks. However, some disadvantages are that it requires more material than other designs, thereby making it weigh more, as well as astronauts' limbs could get caught within the structure and they could injure themselves.
For concept variant 3, it is a deployable design that attaches to the Lunar Gateway. This design uses torsional springs to deploy as well as a latch to hold in place. Some of the advantages is that it is a simple design and mechanism with quick deployment, as well as the disadvantages, which it could have structural instabilities and cause harm to astronauts when deploying.
To evaluate our designs, we developed this plan, which includes 3 stages. The first stage will test all 3 concept variants in its most basic engineering requirements, which include the mass, the antenna height, and a static loading simulation, which simulates the astronaut kick load. The static simulation will also test the strength of the attachment point on both the handrail for the ISS and the external rail for the Lunar Gateway mission. Through a decision matrix, our team down-selected to a single leading concept variant, which will be further tested with vibration simulations and thermal loading simulations. Finally, our team also prototyped a functional model which can be tested in person for deployment and also injury to users through a static loading test. The stage 1 simulations for concept variant 1 are shown here. Initially, there was excessive yielding in both the handrail and the structure itself, but through a series of iterative design changes, which included reducing the wall thickness of the lattice structure, we were able to reduce the yielding on both the handrail and the structure to within the yielding stress of the materials used. The structure was also moved to the side of the handrail where it is more likely to sit in an actual application.
Stage 1 simulations for concept variant 2 are seen here. On the left, there was yielding within the rail of the Lunar Gateway, and through an iterative process of changing the cross-sectional area of the I-beam, the simulation seen on the right was conducted where no yielding was seen anywhere on the structure.
For concept variant 3, as you can see for the first simulation that there is yielding in the hinge. For the second picture, you can see the U-bolt, which is supposed to be for the latch. This was a set point in the simulation, so you can see that there is some yielding there.
In order to decide which concept to prototype, we created a decision matrix. As seen, the criteria on the left was ranked through by their importance, and each design was scored with a score of 1 through 10. The concept variant 3 had the highest score of 180, so we decided to move forward and prototype that design.
Our prototype of the concept variant 3 is comprised of both off-the-shelf and custom parts we created. The total cost of our prototype design came out to be around $350, which is well within our $1,000 budget. The pictures below illustrate the major components used in our design. These pictures illustrate the final product of our deployable structure locked into the latch. This slide has a video that shows our structure deploying into its final upright position. In conclusion, we have developed multiple concepts. Stage 2 simulations and attaching the burn wire and latch onto our prototype are a few additional actions we need to complete, which will be discussed in the final report by December 4th.
We have included our references here for your further consideration. Thank you for your time.
All right, thank you, NASA Mount team. So as our audience has time, please enter questions into slido.com. Use the code TSGC so that the team can answer them. Team, you can turn on your video and unmute if you'd like. So you are one of the few teams that actually completed everything in one semester. You're a one semester team. How was that rapid schedule in terms of teamwork?
It was definitely pretty compressed, especially trying to develop our designs and also get in a prototype. But I think we were able to manage it through just meeting more frequently, and we're all around campus, so that was easier as well.
Were there any issues with your final fabrication?
We no major issues encountered, but we are still working on our prototype. We have the hinge mechanism down, which is the major portion of it. We're still working on a burn wire mechanism, which will act as a release. A burn wire will secure the antenna mount in its collapsed position, and a current will be used to sever the cord deployed into its deployed position. So we're still working on that.
Okay, so I guess that would help eliminate any risk to the astronauts if it's done remotely?
Correct.
Yes, the intention is that it doesn't need any human interference to deploy it. A current Wi-Fi antenna mount used on the ISS requires an astronaut to retrofit and install it after launch. And this way, this antenna mount will be in its folded position upon launch and then self-deployed once it's in orbit.
All right, great. We don't have any questions from the audience yet. Audience, go ahead and go to slido.com, ask your questions for the team. Let me ask about your decision tree there. So concepts 1 and 3 were quite close. Did you ever consider a hybrid of the two?
That's definitely something we considered.
Yeah, to add to that, one of the purposes of exploring different applications and different design features at once is so that we can sort of have a bank of ideas to draw upon for any future missions for our mentor to be able to use. And so we did discuss the possibility of combining design 1 and 2. They definitely fit together, and that would be one option for any future missions to be able to draw upon both ideas.
Okay, so designs 1 and 2, the lattice structure.
Oh, sorry, I meant 1 and 3.
1 and 3. Okay.
Yeah.
All right, great. Okay, here's a question. Did you consider using carbon fiber for your structure? What are the advantages or disadvantages of that?
So we definitely looked at various materials to use for this, including different aluminum alloys, carbon fibers, composite materials. I think the main challenge for a material like that would be being able to have good properties at extreme temperatures. From our engineering requirements, the temperature range we wanted to work with was from 100 Kelvin to 500 Kelvin. And so these materials would need to have good properties at these temperatures, and also good thermal expansion coefficients to work with other components. But definitely that would be a material worth looking into.
Okay, and remind me again, what was your final material?
We intend to use, well, for our prototype, we used aluminum, and that is what the current antenna mount uses. And so we wanted to use that as our base material.
All right, great. So if you had another semester, where would you go with this project?
So we would definitely be wanting to explore further testing on such a device. One major concern is the rebounding from kick loads. If an astronaut does kick this antenna mount, we would want to see how it reacts and if it would swing back and potentially injure the astronaut. So that would require more sophisticated simulations, more than just the static loading simulation. We definitely want to explore different materials and be able to test them at extreme temperatures to see how they hold up. And additionally, maybe explore the other concepts we developed further. I think the lattice structure and the arc structure do present several advantages that are worth looking into more.
All right, great. So how was it working with the team, and what were your biggest challenges?
I think one of our biggest challenges are the virtual meetings and not really having the cohesion as a team due to COVID restrictions.
Yeah, certainly. This semester was a bit challenging, being able to work remotely. But I would say, one big challenge in this situation is, of course, communication, being able to stay in contact with everyone. But we were able to try our best to do that. Just being on top of things in terms of communicating with our teammates, that was a challenge we had to overcome.
Any other teammates have a comment on that?
I would have to agree too with the COVID restrictions of having not enough resources available of utilizing different laboratories on our campus and stuff because of all the restrictions that we have.
We do regret to inform that Jesse was not able to make it today. He fell ill this past few days, and he's been at home sick.
Okay, we wish him well. We've got a few minutes left. Tell us about your design class at UT. How many students are in it? And it's a senior level design, correct?
Right. So I believe there are about
I think there's 6 teams of 4. 16 teams of 4, so about 60 students.
And this is the senior design project. So this is for all of us is our final semester, and it's more of a continuation from a practical application of a previous course we took, where we look at design methodology, everything going from concept generation to engineering requirements to embodiment of our design and down selection. Which is why we utilize a lot of those methods in our project. So it's really helpful to be able to learn about the methodology of design and be able to apply it to a practical application at the same time. And I have the physical prototype here. And it was nice that the campus resources like the machine shop were still open and available to us. So we were fortunate enough to be able to access those and be able to prototype our design.
Well, great. Thank you very much, team. Thanks for participating, and good luck after graduation.
Thank you so much. Thank you for your time, and thank you for the opportunity.
Okay, our next team is from the University of Houston. Team Von Mises, I always get that wrong. In the Q&A, they can explain where their name came from. So for the Q&A, again, go to slido.com, slido.com. Please use the code TSGC and ask your questions for the team. This is the first of our teams that are in the NASA Suits Challenge. That's the Spacesuit User Interface Technologies for Students. We added that as an option this year for Design Challenge, and we're very happy to see a few teams apply for that.
Hi, we are Team Bommies from the University of Houston. Our project is a NASA Suit User Interface Technologies. My name is Ngọc Nguyen.
My name is Nancy Wood.
My name is Ashwin Matthews.
And my name is Amira Shahara.
We are a team of 4 mechanical engineering students. This is our first time participating in TSGC. We've learned a lot during the past 2 months, and we are very excited to share with you about our project. The agenda will be split into 4 main parts. By the end of this presentation, you will learn about what NASA's tasks for this year are, how our design meet those tasks, and our plan moving forward.
In NASA suits, the primary goal of augmented reality or AR system is to assist the astronaut with EVA responsibility in a way that when they are on a lunar surface, they can use their time proficiently and in the best way possible. Navigation, geology sampling, and system states are the 3 major EVA tasks, and our goal is to design a simple and safe user interface that can help the astronaut to successfully complete their assigned missions on the lunar surface. For the navigation part of the operation, the ideal design must meet 3 major criteria. Firstly, the system must be designed in a way that can navigate the astronauts from one desired point to another. The second criteria that needs to be met is that the device has to be able to guide the astronaut back to the lander, as well as telling them how long it will take to go back. Last but not least criteria is that the design must have the ability to direct and navigate the astronaut to the areas of geological interest. For the EVA system state part of the operation, the design system must be able to interact with the suit port to execute the airlock activities such as display and control unit and umbilical interface assembly. Also, in any case of emergency, the system must notify the astronaut to return to the pressurized environment. To ensure the astronaut's safety and the success of the mission, the HMD designed by the team should inform the astronaut by displaying all the information related to the factors that I just mentioned on a screen. For the geology sampling part of the operation, the HMD system must have multiple abilities in order for the astronaut to complete their missions in the safest and quickest way possible. The HMD device must guide the astronaut through the sampling instructions, direction to how to interact and use each specific tool, navigate to the correct side, provide a unique method for taking field notes, take a picture of each sample, and finally a way to collect the samples.
So designing for augmented reality is a challenging task. Augmented reality, or AR, is very similar to virtual reality. However, in AR, components of the design will display on top of the real-world environment in our visible view. Likewise, there are some special considerations we must take to ensure that the AR experience is effective in accomplishing our desired task. The first consideration is something called interaction cost, which is defined as the sum of all mental and physical efforts used to perform a task. In this image, the user's mental efforts involve processing the GPS navigations and applying those directions to their driving, and the user's physical efforts involve operating the car and clicking through the GPS system with their hands. Generally, a lower interaction cost is desired in our UI. Now, the next consideration is something called cognitive load. Now look at the top and bottom lines of text. If I were to show you both lines and ask you to replicate them from memory, you'd probably have more success replicating the bottom line. This is because the brain processes information in separate chunks. You might notice the bottom line features easily recognizable acronyms like IBM or USA. The brain therefore processes each acronym as a single chunk of information, resulting in a total of 4 chunks. The top line, however, features randomly placed letters of differing lengths. This forces your brain to treat each letter as a separate chunk, resulting in a total of 12 chunks. Cognitive load theory tells us that the brain can only handle so many chunks of information at once, and the lower that amount, the better. Now, our last consideration is seamless task switching. Whenever you operate your smartphone, you're very easily able to switch applications or tasks through the app browser. Similarly, we want our AR system to exhibit the same qualities when switching from an operation such as navigation to another such as geology sampling. Overall, we want to keep these 3 theories in mind when designing our AR UI.
In order to design the user interface for the HoloLens 2, we first ideated and brainstormed ideas on how to tackle the goals given by the NASA Suits Design Challenge. Then a user flow map was created to show the overall flow of our user interface design. Lastly, low-fidelity wireframes or prototypes of screens were created in order to test the user interface design. In the next few slides, we'll go into detail about our design for each task.
Here's the AR display during navigation operation. The astronaut will be able to see the destination indicator, which shows the location that they are heading to. Right below that, there will be a distance and ETA timer, showing them how long and how far it would take them to get there. Now, my favorite is the directional hologram, which shows the path where the astronaut can follow to their destination. Those holograms are designed in a way that they are clearly showing the map, but at the same time not too overwhelming so that the astronaut can still see any obstacle on their way. The holograms would follow the shortest route provided by available data, and they will also act as assistant for any elevation changes. And lastly, we have the collapsible map. In this view, the astronaut will be able to see not only where they're heading to, but also any geology sampling sites and points of interest. The orange path here shows the route overview. It's very similar to the GPS navigation system on Earth. And most importantly, we have buttons for astronauts to switch destination or cancel their current route.
When the astronaut is ready to start completing their geology sampling missions, they can go to the geology sampling menu as shown in the image. The geology sampling menu will have the option to either go through a few geology sampling tutorials or to choose a geology sampling mission to complete. Once the astronaut wants to start their geology sampling, they can click on the missions button to fill out a field note to take down their observations. The field note will be able to save qualitative information as well as pictures of the geology sample. The qualitative information such as color can be noted by selecting a choice from a drop-down menu. This will be done by just tapping the desired selection in the drop-down menu. The pictures can also be taken and saved on the field note by tapping the Take Picture button as shown in the image. Also, the astronaut can retake pictures as needed. When the astronaut is done taking the field note, they can tap the Save Note button, which will save their field note.
Now, in the emergency state, the astronaut must easily be able to return to a nominal condition or return to the lunar lander. If the astronaut experiences an anomaly, a screen displaying a warning indicator, anomaly description, along with the tool used to fix the anomaly should appear, if applicable. In the overall design, we attempt to display the key components of the in a non-intrusive manner. To do so, we create a menu that only appears when the astronaut stands still. Now, when this occurs, the full system indicators will appear at the top of the screen. Additionally, the astronaut can access the navigation and geology sampling menus at the bottom corners of the screen.
In order to implement our design into the HoloLens in a timely manner, we create a project plan which we'll talk about in a few slides. The major accomplishments that we have completed and submitted so far are our suits proposal and TSGC midterm report. The TSGC poster that has already been submitted and today's presentation will wrap up our completed milestones. Moving forward, we're planning to submit our final report to TSGC by December 4th. We will have 4 total outreach activities, and those will be held sometimes in months of February, March, and April. Our plan is to have our UI built in HoloLens by February 26th, followed by testing AR usability on March 1st. Also, the human in the loop testing will be held on March 26th, and finally, our final system will be delivered to NASA suits on April 16th.
And that concludes our presentations. Thank you for listening, and we hope to see you later today.
Okay, team, go ahead and turn on your cameras and your audio. And we have some questions already. First one is, when I was going to ask, was your team accepted to the 2021 Suits Challenge?
Yes, we actually found out about an hour ago that we got accepted for this year.
Hey, congratulations.
Thank you.
That is awesome. I guess your timeline still applies since you had to turn that in this week. All right, next question. Do you see this being applied to vehicles such as the rover as well, or would it be more efficient to just have it on the suits alone?
Oh, I can take that question. For us, when we design this user interface, we really focus on the astronaut. That's the attention for them to be able to conduct EVA. As for vehicle, I think it will be really different because the astronaut, they would actively be making decisions and using those things. But as for vehicle, they would have sensors already, and we would have people in mission control to guide them to where to go and what to do. So that would be really different in terms of the user interface we're using.
Okay, next question. I guess it's a basic interface question. How do the astronauts click on the different options?
So I can take that one, I think. So on the HoloLens, there are several different like gestures and actions you can take in order to select something. One of them is called bloom, where you hold your hand like this and expand it. Another is called gaze, where you just stare at an option and then it just automatically gets clicked. To make this process really simple, we decided to go with some pretty familiar actions. So we went with a simple tap action. It's when the astronaut takes their thumb and forefinger and then just clicks them together. And that's what we thought was the best choice for this kind of interface.
All right, great. Next question. Can you describe the meaning and background of your team name?
I have this one actually. This is actually my fault. So last year in our machine design class, our professor was going over von Mises stress, and I think he pronounced it as von Mies stress. And so I turned to Ashlyn and I said, did he just say von Mies stress, like the sandwich? And ever since then, it's been an inside joke.
Okay, so it's von Mies.
Yes.
Excellent. Next question. Are you purchasing HoloLens 1 or HoloLens 2?
Yes, we are planning to get the HoloLens 2. And Suits actually has a program where they may be able to sponsor us to get a HoloLens 2. So we are really excited to send them that email and request to get that.
Excellent. Good luck with that.
Thank you.
All right. Here's the next question. What's preventing the interface from being open when not wanted?
Oh, that's a good question. So I would say when we decide this, we have some components that would be displayed at all times. So those including the suit's vital, how much oxygen you have left in your tank. Also, if you're in navigation, then it would always show how far you are from the destination and where you're going. So once you activated the UI, those things would always be there. But the great things about AR is that even though you see those components, the virtual objects, I call them, you can still see what you're actually seeing in real life. So it's not, when we design those, we're not gonna let those virtual objects block your actual view of what's happening around you. And for our team, we're also incorporating something called a stencil menu, which if you are not in motion, the stencil menu will be activated and you will be able to access all other components in the UI, including, let's say, tutorials or pictures, things like that.
Okay, very good. Next question. Does your tool require any form of calibration for helping you navigate or select features within the HoloLens?
I think as for calibration, I think the HoloLens 2 is already calibrated in terms of all the cameras and sensor with that. From what we got from Suit, they're telling us that they already have some set of data back from the Apollo mission. So what we have to do is that we created this program and we import the available data. and then we put that in, and from there we can start testing and see if it's actually working as intended.
Okay. Next question. Is there any concern about power consumption with the suit, showing so much information every time that the astronaut stands still?
Yeah, that we haven't really looked too into it, but I agree that that may be a concern of getting too much power from it. We will have to look more into what type of HMD device that NASA would actually use. So I believe that for the HoloLens 2, it's just for us to test on Earth condition. When they actually go to Artemis mission, they may need to use an entirely different HMD device, and we have to look into the whole structure of the XEMU overall to make decision and see how much power it would consume.
Okay, next question. Is there a separate system that this design interacts with in order to have the map data? Did you just design the interface system or the mapping as well?
We're not designing the map. We're making this interface with the assumption that it will be connected to the network system. So when I look into this, I saw that they are NASA is exploring some other options such as the lunar net. It's similar to the GPS system on Earth, where you will get like location data at real time. So we're making our design to be based on that assumption of that's what we're going to be connected our HMD to.
Okay, could you explain some of the geological sampling that was one of your requirements?
I think
guess
Nancy can take that.
I guess what we're doing for the geological sampling is mainly with the field note. And one way that we're sort of, I guess, making new or optimizing the field note is by using the using a drop-down menu in order to take down observations, as we discussed in the PowerPoint. We're using the tapping method that Ashwin mentioned earlier in order to select pre-recorded selections, like for color. Instead of saying the actual color, you would just tap down from like a preloaded menu. And the reason why we went with this is because we saw some research saying that voice recorded notes might be inaccurate. I guess that was one of our decision making for geology sampling.
I want to add to that as well. Another major thing about geology sampling is the interaction with the tools. So we know that when the astronauts do EVA missions, they have to carry a lot of tools with them. And so what we would do is that we make sure in our system to show what tools would be needed for each type of samples, and also maybe exactly where the tool is stored so that it would help them quickly get out the tool as needed. If they need to, they can view a quick tutorial of how to actually use the tool, because collecting samples on the moon is not as easy as on Earth. They have to be they really know what they really need to know, like what they're collecting, and be really careful with that. So we want to help them with that process.
Excellent. All right. Well, thank you very much, team. Congratulations on continuing next semester, and we look forward to seeing your next report.
Thank you.
Thank you.
Okay, next up we have San Jacinto College and the SJC Gators. Again, audience, if you could go to slido.com, enter your questions there, and use the code TSGC to access the showcase question and answer session.
Greetings. We are the SJC Gators from San Jacinto College. Our Texas Space Grant Consortium Design Challenge is to create a solar concentrator for extraterrestrial use. The SJC Gators is made up of 4 team members: Damian Leos, John Burback, Ian Ebert, and myself, Michael Kruger. Our faculty advisor is Dr. Nathaniel Wiggins. We have 2 mentors, Mr. Christopher Mendel and Mr. Houston Green. Typically, solar concentrators are designed using either lenses or mirrors to collect and to focus the sunlight. Concentrated solar flux has both thermal and electrical uses. One design option is the parabolic mirror, which has a really high concentration, but the problem we've encountered in the past is that it requires tracking of the sun. So as the sun moves, that mirror has to track it. Fresnel lenses, on the other hand, have a really wide acceptance angle and therefore show great promise if we wanted to eliminate that solar tracking. So why should we put a solar concentrator on the surface of the moon? Well, we could use it to provide energy and lighting for a possible human habitat. We could also use it to melt lunar regolith, which is basically the topsoil of the moon. Within that lunar regolith are valuable elements. There's oxygen, which we could use for the human habitat, and there's also helium-3. Helium-3 has great potential to provide energy. In fact, 44 tons of it is enough to power the United States for an entire year. And it's estimated that there's around 1 million tons of helium-3 on the moon's surface. Designing a solar concentrator for use on the moon comes with its own unique challenges, such as lunar dust. Lunar dust is composed of very small, sharp particles that float around on the moon's surface, and they stick to almost everything. This causes problems for machines that have moving parts because the dust gets inside of those joints and causes them to seize up and to degrade. It also collects on optical surfaces and blocks the light, which is a huge problem for solar concentrators. The temperature on the surface of the moon cycles from 100 to 400 Kelvin. This large variance in temperature can cause materials to crack and deform. Therefore, our lunar solar concentrator must meet the following objectives. It needs to have a wide angle of acceptance to remove the need for tracking and moving parts. It must be able to generate enough heat to melt lunar regolith and endure the large changes of temperature on the moon's surface. It will need to be durable to survive a launch, possible contact with lunar dust, and possible meteorite collisions. A low density is also important to keep costs down, and the optical surfaces will need to be kept free from lunar dust accumulation. On the left, you can see the original design inspired by our mentor, Mr. Christopher Mendel, and on the right is our newest design with several improvements. Our concept involves a combination of lenses and mirrors. On the outside are 2 parabolic mirrors, which direct light onto a cylindrical Fresnel lens. The Fresnel lens then focuses the light onto the rounded edge of a funnel receiver lens, which then redirects the light onto a fiber optic cable.
All right, so I'm going to give you guys a rundown of our Fresnel lens model that we designed. Basically, what a Fresnel lens is it reduces spherical aberration. And spherical aberration is light's error in its ability to focus onto a single point. So you'll experience a spread of light as opposed to just light focused onto a single point. What we did to design this was we used a mathematical program called Mathematica, and we designed a 2-dimensional model in there using coding and formulas. You can see on the upper right-hand corner where we translate this spherical lens into the Fresnel lens along axis lines, and you can see where the ribs were created along those lines. We took this 2-dimensional model to make our 3D model using this concept, and we rotated the model and the sketch around an axis. This allows us to capture light in 360 degrees as the sun rotates in the atmosphere of wherever this will be placed. In our 3-dimensional model on the lower right-hand corner, you can't see the individual ribs in the model because there are 286 of them. The fact that there's 286 ribs allows us to focus the light to a more precise accuracy, and it also allows us to reduce the weight of the lens by making the lens thinner.
I will be presenting the funnel lens. The edge of the funnel lens is placed at the focal arc of the Fresnel lens so as to maximize the amount of light captured. The bottom leftmost photo shows the highlighted area where the light would be directed. It uses internal reflection to redirect and focus the light down the narrow end of the tube, which will head off into a fiber optic cable. On this slide, you can see a hand-drawn ray trace of light entering and reflecting within the funnel. At the top right, you can also see the light entering into the funnel at a wide range of angles. You can also see how the light bends once it enters into the funnel. This is due to Snell's law and the refractive index of aluminum oxynitride. Aluminum oxynitride is the material that we chose to go with for both of our lenses. The critical angle of aluminum oxynitride is 33.9 degrees, and due to the phenomenon known as total internal reflection, any ray that hits at an angle of incidence greater than 33.9 degrees will reflect within the funnel. Of the 9 rays that were hand-drawn, only 1 escaped out of the funnel. The other 8 were successfully contained and redirected throughout it. On this slide, you can see the materials that we researched for our lenses. Aluminum oxynitride, also known as ALON, as shown on the top row, had the highest Knoop hardness, which makes it the most scratch-resistant and most durable on this list. The CTE, or coefficient of thermal expansion, is also relatively low, which means it's able to withstand the fluctuating temperatures of the lunar surface. The melting point is also way above what is needed to melt regolith, which is at 1775 Kelvin.
The mirrors will have a parabolic shape with their focus on the edge of the Fresnel lens. After examining many materials, graphite epoxy stands out as a great option. It has a low coefficient of thermal expansion and a very high tensile strength, which means that it is durable. It is also a great economic choice due to its low density and cost.
When we designed the base, we decided to use a honeycomb structure. This kind of structure helps to minimize the amount of needed materials while also maintaining structural integrity for prolonged use in extraterrestrial environments. Another feature is the optical mounts that provide easy access to the lenses in the event of repair or replacement. We selected aluminum for the structural component of the project due to its low cost of production, low density, high tensile strength, and high melting point.
We've done a lot of research into the optimization of our fiber optic cable design. Recent research has shown the benefits of hollowing out the fiber optic cable and replacing the inside with silica fiber cores. This is beneficial because it reduces the energy loss of light energy into thermal energy with the reduction of mass inside the cable. These silica fiber cores will be shaped in a kagome or hexagonal lattice structure, as you can see on the bottom right-hand corner. This structure is important because it reduces light energy loss throughout the cable because of the high incident angles. The cores can also be filled with compressed gas to actually amplify the light being transmitted throughout the cable, as recent tests have shown. With the continuation of our project, we have a few areas that we would like to focus on in the future. First being our fiber optics materials for the insulation and interior of the cable. We'd like to run simulations to prove the efficiency of our optics. We'd also like to optimize our base design, meaning possibly changing the material and the interior design of our base. This would also include modifying the fasteners and improving them to hold our optics in place and hold our structure in place in extraterrestrial habitats. We'd like to look at lunar dust solutions. One possible solution that we looked into was actually creating a positively charged electric field on the optics and using that to repel the positively charged lunar dust particles.
We'd like to give special thanks to our mentors, Mr. Christopher Mendel and Mr. Houston Green, and to our faculty advisor, Dr. Nathaniel Wiggins, and to the Texas Space Grant Consortium for giving us this opportunity, and of course to San Jacinto.
Okay, team. Go ahead and start your audio and video. Audience, please go ahead and go to slido.com to ask your questions.
Dr. Urban, while we wait for those questions, I'd just like to say that we had a reference slide and it got cut off somehow, but just so if anybody wants to see any of that, I'd be glad to send it to them.
Okay, good. And I'm sure it's on your poster as well. This is a good time to remind everyone to go check out the posters that are online. If you don't have that link, email showcase2020@tsgc.utexas.edu and we can get you that link to the posters. All right, first question. Will this be enough to provide power through a fiber optic cable?
I'll go ahead and answer. We've got the basic design and a good concept, and we're in the process of getting simulations done still. Finding optical simulation software has been very difficult. A lot of it's really expensive, and it hasn't been very accessible to us this far. So we're still in the thick of getting that complete, where we can run the simulations and therefore prove how much energy would be produced by the design. But we have faith that it will be able to provide enough power.
Yeah, and it's also possible to scale the system up and down as needed to create more power and to increase that exposure to sunlight, depending on the size of it.
Okay, good. Next question. How is the Fresnel lens going to be manufactured, creating 260 plus ribs on a less sounds expensive?
Right. So the algorithm that I used to create the Fresnel lens was actually based off of commonly commercially produced Fresnel lenses. So the actual size of each rib is similar to very precise Fresnel lenses that are currently made and used on Earth. So I wouldn't think that it would be extremely expensive as to purchase these Fresnel lenses from companies. It's not very pricey, but it's also very beneficial to have a large number of ribs in the Fresnel lens because it allows you not to rely on the material to bend the light, and it lets each individual rib have its own angle towards the focal point and reduce spherical aberration.
Okay, remind me, what size are we talking here, or is it completely scalable?
It's completely scalable.
It is scalable. In the deliverables of the abstract, they asked for something that could deliver between 10 and 100 watts. However, I think the end game is, if we wanted to decompose regolith and get those gases out of it, we were talking about kilowatts. So, I guess the concept was just to try to get a prototype going, and then to scale it up for other uses.
Great, thanks. Next question here. What are the primary manufacturing methods you will use to construct other parts of the design, the base, support structures, etc.?
Manufacturing of the base. Well, I haven't been to a machine shop yet. I mean, I always just kind of envisioned that we would send a design off to and then, that it would somehow just be machined, but I don't know what else to say in response to that question. I guess that's kind of a hole in my knowledge right now.
Right, and there's companies that make lenses out of A-Lon currently, so it'd probably be good to reach out to some of those companies to manufacture our lenses.
Yeah, in terms of getting the materials, Cermet, I think they've got they're the ones who think they've got some sort of almost a monopoly on aluminum oxynitride, or they're one of the main producers. So we would definitely need to contact them about getting the material. I do know about with the mirrors, using the graphite with the manufacturing, the machining of that is actually somewhat, it's a little bit difficult, and it involves creating a mandrel and then running that mandrel over the surface of the epoxy to smooth it out. So the machining of the mirrors with that material is one thing that is a little bit difficult.
Okay, and let me just ask about cost then. Is the Alon high cost? Yeah, I didn't see that on your list of materials.
Well, as far as I've been able to find so far, it is relatively high cost. That'll definitely have to be a forward work to contact CERMET. And, I think part of we were still, since we hadn't yet created a prototype, kind of unsure of exactly how big it would need to be. And then that would really influence kind of how expensive of a material you could use. But we'll consider that definitely a forward work to contact CERMET and try to get a cost per kilogram of Alon.
Right. And because of the extremely high durability, we believe that because of its prolonged life in comparison to other lens materials, that it would be beneficial to use that instead of having to replace a lens or send up another more material.
Do you have an estimated design life?
I guess we currently do not. We use the parameters that we knew to use to try to maximize the life, but haven't yet figured out how to estimate that. With that low coefficient of thermal expansion, it should definitely help extend the life. I mean, the goal was, so that to choose materials that wouldn't crack and things like that, so that it wouldn't need to be serviced very often. That was definitely one of our main, a huge primary consideration with the materials.
Now, if this, for example, was going to be deployed on the moon, how much would dust impact your collection?
So the lunar dust sticking onto the lens is a big problem that we looked at, which is why we're looking at solutions for our future studies. A very promising one was creating that electric field on the lens materials and the optical materials to repel lunar dust, and it's shown to be very effective in studies.
Yeah, because the lunar dust is, most of it is positively charged because of the photoelectric effect of the sun's rays hitting it. And so the idea is to get, recently there have been some findings or developments where they're able to create transparent conductive coatings that are transparent, and then we could hopefully somehow charge that coating and with a positive charge, put a positive charge on it, and it would keep the lunar dust, it would repel it. The like charges would repel. That's at least in theory, but it's definitely it's tricky because we don't have lunar dust to test it out here on Earth, right? So you kind of it's one of the difficulties.
All right, great. And then last question. So what challenges did you encounter this semester?
I think definitely one of the big challenges is how COVID affected us meeting each other, and just finding different dang, I forgot the word. Finding different simulations to use because most of them were out of our price range, and most of them didn't want to give us a chance because we're college students and don't have money.
Yeah, and yeah, you know, a lot of the other teams have said, you know, meeting virtually slowed them down and made it more difficult. We were looking at 3D printing some of our parts, and so we were looking at using the library as a possible resource, and their 3D printing was closed. And San Jacinto College, we couldn't go into the lab there to do any work, so that was another obstacle that we just couldn't overcome. And then you know,
I think working with optics has also made it difficult to create a physical prototype of any kind. Fresnel lenses, to your specifications, are pretty hard to get a hold of and to manufacture, at least individually. So that just made it difficult to build a prototype.
Understood. All right. Well, thank you very much, team, and good luck next semester.
Thank you.
Thank you.
Okay, this ends our second session today. We'll take a 10-minute break and come back at 3:40. Good afternoon and welcome back to our third and final session this afternoon. We have 3 more teams coming up in this session. First up, the University of Texas at Tyler, Team Vanguard, or HEC 23. Again, audience members, please go to slido.com to submit your questions and use the code TSGC.
Hello everyone, thank you for joining us this afternoon. My name is Antonio Mejia and I am the team leader for Vanguard from the University of Texas at Tyler Houston Engineering Center. On the team with me are Monica Moncondui, our co-leader, Zachary Butterfrost, our communications officer, and our designers, Michael Myra and Amin Marashi. Together, we're working on the Lunar Surface Extravehicular Activity Operations Spacesuit Attachment Quick Release System. We are under the advisorship of Professor Aus Al-Shalash, and then we're working in tandem with our partners from NASA Johnson Space Center EC Group. I will pass the ball over to Michael Myra, who will tell you a little bit more about why we are here today.
Thank you, Antonio. Now our concept statement. To design 2 interlocking components with a quick release for a spacesuit utility belt that secures tools required by astronauts on spacewalks. Now, throughout the presentation, orange will refer to the male end and blue for the female end. Applying a quick release attachment for an astronaut to connect and disconnect their tools quickly, smoothly, and repetitive will increase the efficiency of a spacewalk. Now, here is a picture of a spacesuit and the location of where the utility belt will be located. Here is our presentation layout. Each section discussed is identified by a color marker. Background information. The Artemis program will be sending the first woman and next man to the moon in 2024. The astronauts will be landing on the South Pole region of the moon, where they will be mining for ice. Now I will pass it off to Monica to discuss the specifications.
Thank you, Michael. We broke our design specifications into 3 different categories. Starting with what you see on your screen is quantitative, then we'll look at qualitative, and finish up with safety. For the quantitative you see on your screen, the 3 I would like to point out is our assembly volume of maximum 48 inches, assembly weight of maximum 2 pounds, and the actuation stability of minimum of 6 pounds. You see there's a strong focus on making it as small as possible, but also something that won't be activated too easily. The qualitative design specifications are a little bit more intangible. They focus mostly on the operations of the tool itself. We want the astronauts to be able to reach behind them without looking, disconnect the tool, and be able to use it without any worries of lunar dust or limited dexterity. Safety design specifications are of the utmost importance. You'll notice we focused on minimizing sharp edges and pinch points, as well as eliminating any possible spots for entrapment of fingers. You'll see how these design specifications came into play as Zachary walks us through our concept.
Thank you, Monica. Here we have our Vanguard XCMU quick release and catch system. The animation on the right shows the motion of the mechanism. The male end, displayed in orange, is attached to the tool and will slide down into the channel of the female end, displayed in blue, which is attached to the utility belt. As the male end meets the rollers, they will push apart and reform around it with the help of 2 torsion springs, securing it in place. Here we have the exploded view for our quick release assembly. Starting from the tool side on the left to the belt side on the right, we have the male end, 4 number 10 screws which secure it to the tool, 4 number 2 screws which secure the cover plate itself, the double roller catch with its 2 torsion springs, 4 number 10 screws to secure the female end to the belt, and the female end itself. The double roller catch subassembly inserts into the bottom of the female end and is then secured by sealing the cover plate onto the opening. This will help to prevent dust from reaching the latching mechanism and ensures that it is stationary. Here we can see the latch with its springs. As the male end pushes down on the rollers, they will separate, and as it moves past, they will then reform from the force of the springs in compression. A finite element analysis was performed on the areas of the two parts under the greatest load. As anticipated, the weakest part was the cylindrical rod on the male end, which started to permanently deform under a maximum load of about 47 pounds. This gives our device a current safety factor of 3.14 based on the male end maximum load and the 15-pound minimum load requirement. With that, I will hand it off to Amin so he can discuss the requirement compliance matrix.
Thanks, Zachary. Here we have the requirement compliance matrix for this concept design. The quantitative requirements are easier to measure compared to the qualitative ones. Our design is able to support at least 15 pounds and it fits within the specified volume. The design only uses manual power and it weighs less than 2 pounds. This design should be operable outside of the astronaut's line of sight, and it should be able to function when it's fully submerged in moon dust simulant. To test if our design is dust tolerant, the team intends to use flour and sand as substitutes for moon dust. Another important requirement is that the two pieces should mate together with little force and they should stay in place while the astronaut is walking or bending. Also, this design should be operable with EVA glove hands, which will be tested during the prototyping phase. This design should not have holes or openings that could entrap fingers, and that will also be tested during the prototyping phase. Now I'm going to hand it over to Antonio, who will explain more about our budget plans and prototyping process.
Thanks, Amin. In order to develop a comprehensive budget, the team needed to consider a couple of key elements. Things like the manufacturing cost, or the total amount of labor hours involved in machining a given part. In addition to this, we also need to have in mind the cost of materials like aluminum, stainless steel, and Teflon, which are considered in scope for the design, but things that are considered out of scope as well, as they fit within the 3D printing prototyping phase. Things like the cost of polylactic acid. And so what is shown is the total cost per unit kilogram of these materials. External to these materials, we also have certain mechanisms or certain elements in our design, things like steel torsion springs or perhaps compression springs. And so the cost of those need to also be considered. After printing one of our prototypes, we used the total mass of PLA that was utilized in order to price out the total cost. And so what is presented here is a minimum cost of $13.76 for printing of a single prototype. All of our prototypes have been produced on a Dremel Digilab 3D45 printer, which can handle various polymers, including polylactic acid, ABS, PETG, and nylon. Using the 3D printer gives us a degree of flexibility in order to confirm our system's functionality and to ensure that all of the mating or moving elements properly fit. Should the team identify design weaknesses, we're also able to pivot relatively quickly into redesign mode and re-prototyping mode to make sure that our new solution fits within the design framework. On the following slide, you see several images of the various components of our design that have been produced using a 3D printer, including the catching mechanism, the female attachment, and the overall full assembly. In terms of manufacturing, we'll likely implement a couple of different techniques, such as laser cutting, machining, lathing, sheet metal forming and welding, as well as sourcing some materials on the open market, things like springs, tubing, or rod to make the connectors. To protect all of these pieces, we also intend to apply a surface treatment of Teflon to all of our moving parts to preserve the overall lifetime of the system, as well as to reduce friction and to mitigate dust accumulation. Recently, the team completed its first of several outreach activities with a service project at the Armand Bayou Nature Center, a nonprofit organization in the Clear Lake area. The Nature Center promotes STEM education with a focus on earth sciences, and to support the Armand Bayou Eco Explorers program, the team took on the challenge of restoring a rundown footbridge which connects the center to a wildlife observation platform. We were involved in every single stage of the process, including safety training, planning, drafting, measuring, demolition, and construction. Together, we were able to learn more about working as a team and put to practice our much valued engineering education. Next, we plan to participate in the Prairie Pandemonium, a root planting and sustainability project to aid in maintaining the natural ecosystem of the area.
Our current outreach plan includes 5 events, starting with this semester and going throughout the spring 2021 semester. We look forward for the opportunity to engage more with our local communities and schools. The Vanguard team from the University of Texas at Tyler would like to thank you for your time and listening to our presentation. We welcome any questions or comments you may now have.
Okay, thank you, team. Go ahead and turn on your camera and turn off your mute. And we'll ask you some questions. We've already got some here. So in your design, did you consider the electrostatic properties of your materials?
Okay, yeah, no, so the materials were predefined by the MicroG Next Challenge. And so those were aluminum, stainless steel, any industrial grade aluminum. Teflon was also part of that. And so those are materials that have been selected and are fit for purpose for the manufacturing and design.
Okay, what are the rollers made out of, and how do you think they will handle the lunar dust?
Good question. So the rollers are currently planned to be manufactured out of a Teflon rubber, Teflon polymer. And in terms of dust mitigation, well, Teflon itself is a hydrophobic material. And so we're relying on the hydrophobic properties or the surface properties to mitigate the accumulation of dust. I don't know, Zachary, did you want to add on to that?
I think you covered it pretty well, Antonio. The 2 rollers are going to be constructed out of Teflon to help cut down on the friction and the dust accumulation.
Okay, next question. What part of the mechanism keeps attachments from accidentally being released from the clamp under force?
So the team is currently starting to implement a safety locking feature, like a kind of consider it like the safety on a firearm. When it's in the horizontal position, it's an indicator that the lock is in place and the tool physically cannot come out. This is kind of more for when the astronauts going through strenuous movements and stuff like that, and when they get to the job site, they'll be able to disengage those safeties and use them as they see fit.
Okay, we don't have any audience questions right now. Let me ask what your biggest challenge was this semester.
For the project, it's dust. The dust accumulation and getting into moving parts and stuff like that is a very real concern of ours, and a lot of what we're doing is geared towards just mitigating as much dust as possible. Teflon spacers between our moving parts, Teflon coating on all parts that we anticipate will have friction, like the female channel, the latch itself. So dust is a real challenge for us.
I can add on to that. I think also from a project management perspective, we're involved in another challenge for MicroG, and we're applying to that. So managing those different work streams that are involved with making sure that we're delivering on every single expectation for each of the challenges, in addition to all of the coursework. On top of that, right, the restrictions on social distancing with COVID and our desire to really deliver on a quality product. That in itself is a challenge. Being able to really feel like a cohesive team, despite these restrictions on meeting or being close to one another. I think we were able to overcome that going out to the Nature Center to really do an activity as a team, and really being able to break down that barrier.
That looked like a great bonding experience, yeah. When do you find out about MicroG Next?
December, yeah?
Yes.
December, I don't think we have a date yet.
Okay, So have you submitted your application to them?
Yes, sir.
Okay.
Our application, our proposal, all the deliverables.
All right, great, great. We've got a couple more questions here online.
Okay.
Does the EVA tool attachment piece spin freely while in the belt piece?
Yes.
Yes. Go ahead, Antonio.
Yeah, so I have a prototype here with me, so maybe turn off the virtual background here so you can see it. The piece does rotate without any obstruction. So, and it comes out, latches in place.
Looks like it works really well. Yeah. Next question. The male connector appears to be made from one component. What measure are you implementing to minimize breaking from shear stress?
So our primary measurement, we had a problem with this initially. The rod was too small and it bent. It still met the 15-pound requirement, but we felt it bent far too easily. From here, it's really just increasing the size of the rod since we can't really change the material it's made of. But beyond that, that's our measure.
Okay. Increasing that diameter, does that increase the risk of getting a finger stuck in there?
It shouldn't. We'll find out more when we start testing that with that prototype, because we can test it with a gloved hand. But when we increase the diameter, it's such small increments that it increases it to, now it's 0.03 inches greater, but that'll allow it to hold an extra 5 to 10 pounds, something like that. So we don't anticipate that being a problem, but we'll find out in the prototyping and testing phase.
All right, great. Any other questions from the audience? All right, good luck, team. Thank you for presenting and hope to see you next semester.
Thank you.
Thank you. Appreciate it.
All right, while I still have the slide on this screen, I wanted to talk about the MicroG Next program. So with Design Challenge, most of our topics come from NASA Johnson Space Center engineers, led by George Salazar, who provides most of our topics. 2 years ago, we added the competition MicroG Next. That's the MicroG neutral buoyancy experiment, where teams from across the nation get to apply to work in the neutral buoyancy pool there. We had a team from Lone Star College that was a participant 2 years ago. They started with Design Challenge, got accepted into MicroG. Their tool was eventually designed, refined, sent to the space station, and used last year in a spacewalk. So these contests, these students are making a real impact on what's going on with NASA. All right, our next team is from the University of Texas at Austin. They are the super seniors. Again, students, as you get promoted to panelist, please keep your videos off and stay muted until your video is over. Audience, at any time, you can submit questions via the Slido app, slido.com. Use the code TSGC.
Welcome everybody to our presentation. We're the super seniors out of the University of Texas at Austin, and our project is over luminous navigation markers for lunar surface EVAs. So what we'll be going over today, we'll start with an introduction to the team, we'll go over the project background, the concept of operations, as well as the design concept, risk and safety factors, as well as some challenges we ran into, and we'll end with the project budget and timeline. So for our team, I'm Lauren, and I will be going into the Air Force OTS after graduation.
My name is Robert. I'll be graduating in December and commissioning in the Navy.
My name is Briggs, and I'm currently a pilot select in the Air Force.
Hey guys, my name is Jorge, and I'm currently a flight attendant for Republic Airlines based in Miami, and I've co-opted at Delta Airlines Engineering.
All right, so our main problem that we're trying to solve is for navigation on the moon when you can't just use line of sight navigation, and there's no GPS system currently in place for the lunar surface. So there is a need for these navigational beacons that will allow for wayfinding on the moon. Our concept of operations is to have small beacons that astronauts can carry with them and drop along the way as they go for the first time to whatever their target destination is, and then these beacons will stay in place for future EVAs.
The beacon will be a pyramid shape with 4 telescoping legs and an LED at the very top point of the pyramid, attached to a smart microcontroller and radio transceiver that will allow it to behave as a proximity sensor. The microcontroller conserves battery power by allowing a low-powered LED to blink at a set interval depending on the distance between the beacon and the astronaut, and to completely turn off once the astronaut is out of range of sight. The beacon will be deployed by the astronaut pulling out the telescoping legs using a tool and pressing a quick release button that will release the solar panel petals and allow them to hang at a 90-degree angle with the moon's surface, which will be an ideal angle to collect sunlight on the moon's south pole.
The 3 main risk factors that we had to focus on were 3, 9, and 5. So for number 3, that was making sure that the lunar soil didn't damage any of the components inside the beacon. And we solved that through using telescopic legs in the design, and we show that later in a field test. Number 9 was ensuring optimal angle for the solar panels to receive sunlight. And that was also solved through the design and is shown later in the assembly video. And lastly, our main issue, number 5, was our power issue. And George was able to solve that through the electronics design, and he's going to touch on it more now.
One of our biggest challenges is power management. It's also one of the mission requirements to be able to operate on just the battery for 2 weeks or 336 hours due to the solar night. The table above details the total power required to operate the beacon. At our current power budget and battery selected, the time until depletion varies from 27 hours with the LEDs turned on continuously to over 2,000 hours when placed in sleep mode, as can be seen in the table below. Our power management strategy would be to only turn on the LEDs of the beacons that are in range of our astronauts. This will be accomplished by employing a sleep timer and an interrupt sleep mode. For example, when the beacons are in range, they would be on an 8-second sleep timer, which means that only 20% of every hour would be devoted to drawing the 55 milliamps at full power, giving our astronauts over 10 hours a day to work near these beacons. When they are out of range, the interrupt sleep mode will maintain the current draw at a low 580 microamps. Let's see a demo of this in action. The breadboard on the right is our beacon, and it's currently in interrupt sleep mode where it's consuming 585 microamps. To the left is our transmitter, and it's currently disconnected. Once our transmitter is in range, or it's powered on, then the sleep will be interrupted and the LED will blink for a couple of seconds. After which it will go to sleep on the watchdog timer for 8 seconds, wake up, and listen for a new signal. If no signal is found, it will go into the interrupt sleep mode, where it will stay until it finds a new signal. So let's see what happens when a transmitter comes in range. Let's change the setting to milliamps. So here you see it woke up where it's consuming 12 milliamps until a signal is found. Then it goes up to 59 milliamps at full power when the LED is turned on. Here we see it go into the 8-second watchdog timer sleep mode, where we get the best power savings at a rate of 390 microamps. Then the cycle begins again. It wakes up, listens, there's a signal, so it powers up the LED and it goes back to sleep. Now if I disconnect it, it will go back to its 8-second nap, and when it wakes up and there's no signal available, it will slip into the interrupt sleep mode where it consumes 580 microamps. But it's really quick to be interrupted, so as soon as the signal is in range, then it goes right back to the lighting condition. In order to meet this challenge, we resorted to destroying the onboard LED, thereby saving 2 milliamps and an order of magnitude. The astronauts would have the same microcontroller and lower radio transmitter embedded in their spacesuits, or they could have a very small puck-like device that houses a microcontroller, transceiver, and a small battery attached to the outside of their spacesuits with a small carabiner or similar attachment device. Once a device has been deployed, the beacon will use a lower radio to communicate with the puck attached to the astronauts. The distance between the puck and the respective beacon will determine the lighting configuration at the top of the pyramid. We'll use the RSSI, or Received Signal Strength Indicator, on the receiver to determine if the astronauts are in range of the beacon. This RSSI is a negative number measured in decibel milliwatts that ranges from -45 to about -135 on our lower modules, and it gives us a rough estimate of our distance. Basically, the closer we are to 0, the closer we are to the device. The further from 0, the further away from the device. Let's see how this works. So here we're receiving the signal and storing it in our incoming stream. But now we're parsing the data for the RSSI and SNR values and storing them as integers in order to perform comparison operations on them to change the lighting configuration of our beacon. So I've set up this threshold of -50 in order to demonstrate the proximity sensor at a small scale. And if the signal strength is less than or equal to the threshold, then we'll light up our green LED 3 different times, so it'll blink 3 times green. But if the signal strength is greater than our threshold, then it'll cycle the red LED once. We've also set up an LCD on our test rig in order to monitor the signal strength and perform some range tests out in the field. So when they're close to each other and the RSSI value is greater than our threshold of -50, then it'll blink red. But if I move it away, it'll start blinking green as our signal strength drops below our threshold of -50. And when I bring it back, it'll go back to blinking red.
So for our prototype design, we made CAD models that were made as separate pieces and were designed to be assembled post-print instead of printing the entire beacon as a whole. The main challenge for the 3D models was designing the hinge deployment mechanism, and we decided to utilize a pin release lock system. However, we were unable to run through enough iterations of the design to get the deployment mechanism working at 100%, and you'll see this in the next video.
So this is a quick time lapse of the assembly of the internal casing for the beacon. This second time lapse is for the outer petals and some modifications I had to make to the beacon. This is the beacon fully opened up. And this next part is the beacon at a fully deployed state to collect sunlight on the moon. Here's a rough example, the first iteration of the pin release function.
To test the beacon, we did a drop test in sand, and we also tested the range of the lower radios and the visibility of the LEDs as seen in the following videos. Here's a video of the drop test we conducted. We dropped it from about 2 inches to simulate about a foot on the moon, which is what we calculated the astronauts would drop it from. As you can see, it does not sink into the sand very much at all, and it holds up pretty well.
We performed a range test and were able to get about 1/3 of a mile in the suburbs of Houston without line of sight. We also performed a visibility test, and despite it faintly showing up on video, it appeared clearly to the naked eye, even in the light-polluted city of Houston.
This budget report shows the price per beacon. We built 5 working prototypes for our field test, and we also encountered some challenges in sourcing some of the parts, so we had to make changes from the original microcontroller, lower radio module, and some alternate LEDs that we had designed for. Ultimately, we were able to maintain the essence and intent of the original design in spite of the challenges. That concludes our briefing. Are there any questions?
All right, thank you team for your video. We already have a question online here. First up, what level of redundancy is in place to mitigate failure of individual beacons?
So the plan is to store a lot of these smaller beacons. So in the case where one beacon fails or there's partial failure, it's intended to have multiple sets so you can go out and replace that one beacon if necessary. Additionally, the beacons are relatively easy to open up and repair, or at least they can be made in that way.
Also, there's a retroreflective material so that if a light was shined on the beacon and the LED wasn't working, then it would still be visible.
All right, great. Yeah, they also seem to be fairly inexpensive as well. How much does one of them weigh?
Just about half a kilogram, actually, just under that.
All right, next question. How will you keep lunar dust from accumulating on your solar panels and LEDs?
So the telescopic legs make it so that the beacon is about 20 inches off of the ground. I don't imagine dust being kicked up super high, but obviously I've never been to the moon, so I don't know. But if lunar dust does collect on the solar panels at the outside of the beacon, they can just replace that beacon for the time being and take it back and clean it off. But the internal of the casing is completely sealed off, so none of the electronic components will get dust inside of them.
Okay, so an astronaut could essentially deploy one and later just pick it up, shake it off, and put it back, right?
Yes, sir.
Okay, perfect. So what was your team's biggest challenge this semester?
So there was a couple of challenges. Well, a big challenge was we couldn't really get together. I'm based in Houston, and then the other team, the rest of the team is all in Austin, so I couldn't really travel out there and do tests together. But personally, I was working with the electronics, and power management was a big issue. Also, trying to get the correct LoRa radio to work on these microcontrollers. We originally had designed for different components, and then we ran into some kind of logistical issues. We had to source parts from a specific vendor, and their lead times were way too long for the short time we had. We had like 3 weeks to do this from the time of our preliminary design review until now. So I actually had to buy some of these parts on my own. So kind of the budget was kind of an issue also, and the money, unfortunately. But as far as like the hardware goes, yeah, staying within that power budget was hard. And I was able to manage that through coding and also through removing the onboard power LED that saved just enough to get into the microamps level of power savings.
I would also say on the printing end, the printing was free at the UT labs. However, there's a strict set of limitations due to just everything that's going on. So we could only print a handful of pieces a day, and we kind of had to wait for everything to come in before we could assemble it and see if all the pieces fit, and then redesign the CAD fits to try to reprint, etc. So the timeline was difficult.
I can imagine. So you're also one of the teams that has a 1 semester start to finish. And you're all graduating, is that correct?
I believe 2 of us are, and 2 of us are graduating in the spring, sir.
Correct.
All right, good. Does the audience have any other questions? Go to slido.com, put in the code TSGC, and ask your questions. So what's your estimated lifetime for one of these?
We were generally counting on the beacons lasting about as long as whatever the mission required. So if it was a short mission, they would probably stay on the lunar surface they could stay there for up to a few months without needing to be repaired or cleaned off. But they could also last for much longer. The decay of the solar panels would allow for up to 2 years, I think, on the surface.
Okay, great. Let's see. So as far as teamwork, I know, Jorge, you were in Houston, the other three were in Austin. Were you able to get together at all or only on Zoom?
I was only able to get together with them on Zoom, but the rest of the team, I think, got together once. I'm not sure.
Briggs and I got together whenever we conducted the drop test and finished up putting our prototype together, and that was the only time that we had gotten together in person. Other than that, we primarily just used Zoom to communicate and have all of our team meetings.
All right, we have another question here. Any plans to transfer the sensors to a PCB design to have printed?
Yeah, actually, going forward, that would definitely save some size. Right now, it's on a breadboard, and even still, even though it's on a tiny breadboard, it fits inside of our design. All of the components fit together. But yeah, having it on a PCB would definitely be ideal, and further iterating the way that we mount it inside of it can also be achieved. Yeah, but that was definitely in the works. I was looking at that. It's just the ordering the custom PCB would take some time also, and time was something we were really short on.
It is a very quick timeline to do everything in one semester.
Yeah.
Especially finishing before Thanksgiving.
Mm-hmm.
All right. So do you have any final takeaways that you would share with the other teams?
Well, like I said, this is an iterative process, and the fact that we got the beacons to be able to communicate with the astronauts was a kind of a first step, proof of concept. But there's a lot of cool ideas that are in there. Like, for example, in the future, we can set it to where the beacons can send over device health to the astronauts. And it could say like, oh, well, this one is running low on battery if it's already day 8 of the night cycle. And you can go and swap that one out, because the idea is that they have these such as like breadcrumbs, where they, like Lauren was saying, you go and you place a lot of these beacons on your path. Well, on your way back in your buggy or walking, you can just take one and then put a new one there. And it also can tell you if, for example, you're inside of a crater, and then the other astronauts like on the other side. It has a range for up to 10 kilometers. I was only able to get 0.3 miles in Houston, but yeah, it can tell you if somebody's nearby, like if astronaut B is nearby, you can get an indication of that. So, but yeah, that's just like going forward, doing other cool, neat things with the radio communication.
Excellent. Well, great job, team. Good luck in all your future endeavors.
Thank you.
Thanks, sir.
Thank you.
Okay, next up, the last team of this afternoon is from Texas A&M University. They are the 12th Eclipse. Again, for the audience, you can go to slido.com to submit your questions. Use the code TSGC, and you can enter them as soon as you have one while watching the video.
Hello everyone, thank you for attending the Texas A&M 12th Eclipse Team's 2020 TSGC Design Showcase. My name is Lauren Brady and I am the team lead for this project. Also on the team are Matt Rodriguez, the deputy team lead, Van Le, and Michael Rakowski. I would like to take this time to thank our team's advisors, Dr. Chamitoff, Lei Wong, and Neil McHenry for their support. Our team's design goal is to create an AR application on the HoloLens for assistance with intravehicular activity procedures, including ISS maintenance procedures, experiment and research tasks, and documenting items in storage. In addition, we are incorporating a telepresence whiteboard to allow mission control to provide real-time support in the AR display of the astronaut. Our team is part of the 12th Astronaut Lab, home of the Texas A&M NASA Suits team. Our design builds off the user interface panels designed for NASA Suits competition, but are reimagined to provide support for IVA procedures rather than lunar operations. The first design feature our team developed are the maintenance panels. These panels are transparent and can be set to either follow the user or be placed in a static location. These panels are preloaded with the task procedure that the user can iterate through as they complete them. There is also a diagram view, where the user can open interactive 3D models of the task they are working on. This video shows a simulation of snapping connectors together. The astronaut is seen placing the panels in the space while they are working in order to reduce clutter in the field of view. You can also see how the astronaut goes through each procedure and is also able to open the diagram panel and interact with the 3D models of the connectors that they are working on.
Our UI revolves around conducting experiments and other various tasks in an IVA laboratory setting like the International Space Station. One of the most important jobs for an astronaut in the ISS is to conduct experiments for NASA and its clients. Just like laboratories here on Earth, the researcher must conduct an experiment with a specified series of steps. Therefore, we developed an experiment panel that allows the user to identify and select simply by looking at the UI and pinching their current experiment and their current step while also tracking their progress. This can be seen on our full detail view panel on the right. Additionally, our experiment panel allows for models to be displayed that might pertain to the experiment being conducted. We call this our diagram panel. This design feature gives the individual conducting the experiment an ability to cycle through various diagrams which can alleviate time consumption and confusion. Finally, we acknowledge that when an astronaut is conducting such an experiment, they might want to choose a less obstructed panel. We added a smaller but equally beneficial panel just for the current experiment and the current step. This panel can currently be seen to the right. Overall, our design is tailored to the idea that our UI can be present during preparation stages and experimentation without interference.
Howdy, my name is Matthew Rodriguez. I'm the Deputy Team Lead for the 12th Eclipse, and I'll briefly be summarizing the growth of protein crystals aboard the International Space Station. To kick it off, we have to ask ourselves, why are we growing these crystals in the first place? By no means is this a short process. It takes 6 months and is very expensive to send all this laboratory equipment up into space. Typically, protein crystals are grown in a laboratory environment so that they can be harvested later for use in the medical industry, and this can be used to treat a wide range of diseases. The reasons these crystals are being grown on the ISS opposed to on home soil is that during the crystallization process here on Earth, the natural gravitational constant causes convection currents to disrupt the structure during crystallization, and this leads to imperfect samples. Whereas in a microgravity environment, these currents are absent. This allows for the protein molecules, all of which exhibit a random motion due to their natural vibration, to slowly migrate towards growing a crystal structure, producing a much larger, more perfect sample that can be studied here back on Earth to further aid the medical industry.
This video shows the simulated experiment of growing protein crystals on the ISS. The procedure being followed is to take the protein solution from the first Petri dish and add it to the protein molecules in the second Petri dish. Finally, place the crystals under the microscope to check that they have fully formed. The astronaut is shown using the multiple panel display settings and location options to customize the information shown in a way conducive to the experiment. The full detail view and diagram view are beneficial as explanations of the procedure, while the current step view is less obtrusive and easy to display while completing the experiment. These panels will save time spent referring back to procedures and will give astronauts a more interactive and efficient method of completing experiments. This design will also increase the ability to communicate with the experiment designers on Earth through the virtual whiteboard, whose capabilities will be displayed next.
Howdy, I'm Neil McHenry. The 3D Telepresence Whiteboard is a unique new feature we've developed that allows Mission Control to remotely guide astronauts during intravehicular operations using splines and holograms in 3D space. Instead of having to solely rely on an audio loop for task assistance, such as in the past, the IV crew member will now have customized visual cues floating in front of them, guiding them through each task. This technology helps guide the astronaut visually through any drawing that a crew member or mission controller may create. As can be seen in the video, the primary tool for remote annotation is the spline pen. The remote user may freehand draw in any shape, as shown in the virtual ISS connector procedure simulation. This virtual 3D whiteboard can help with navigational cues as well as demonstrations where objects should be placed. The whiteboard has undo/redo functionality as well as options to change drawing color and size. Lastly, the astronaut's visor in the field sends back crew member transform data as well as scan environment mesh data. This makes sure that Mission Control will have situational awareness of the area surrounding the astronaut at all times.
To assist with storage accessibility on the ISS, our team has developed storage panels. These panels are tied to a specific storage container and contain 3D models of the contents of that container. These panels reduce the amount of time spent searching for items in storage and make it faster to search multiple bags by simply opening their respective panel. This video shows the astronaut searching the contents of a storage bag in the multi-purpose module. The contents are displayed in a page view with interactable 3D models and appropriate labels displayed.
For the outreach activity, we present to you Spark, an online learning interface about all things aerospace. In the interface, we talk about the profession of an aerospace engineer. What exactly is an aerospace engineer and what their responsibilities are? We also discuss the ever-increasing importance of aerospace engineering and how it truly is an all-encompassing interdisciplinary field. The interface then dives into different interactive modules where students are walked through simple experiments and activities that demonstrate the various jobs of an aerospace engineer. Some of our modules include straw helicopters, marbles on trampoline experiment, and air-propelled rockets. In every module, we try to foster as much creativity and independence as possible by letting the students take ownership of their designs instead of providing them with a cookie-cutter solution. At the end of each activity, students will have the option to share their designs.
One future goal for this project is to incorporate AR overlays on hardware to further assist with maintenance, repair, and assembly tasks. The Texas A&M 12th Eclipse team would like to extend our sincerest thanks to our advisors, collaborators, and TSGC for their support during this project. If you have any questions, we will be at the team meet and greet this evening, and feel free to contact Lauren Brady, whose email address and phone number are listed below. Thank you for attending our presentation, and have
All right, team. Great video. We have a question from the audience already. What is the background of your team name?
An eclipse is symbolic of growth and a period of transitional change. So this is
Many of our team members were undergraduates and were younger students, so we're using this project to grow and develop our skills as we progress through our college career. Also, the 12th part is the name of the student body, the 12th man of the Texas A&M.
I think they help during football, right?
Yes, we all stand during the football games.
All right, so in the video, you mentioned that you worked with the team on NASA suits. How did that interaction work with two different teams?
Yeah, so we're part of the 12th Astronaut Lab, which main team is the NASA suits team. So they have been working last semester on some of the UI panel functionality you saw. So we kind of took that project as our baseline and worked on really transforming the functionality of those UI panels to better benefit how an astronaut completing an IVA procedure would be. So we redesigned the size and shape and content displays of those panels. So yeah, the NASA suits team was really a baseline, like springing point for our team to really develop those panels and the whiteboard capability to assist not EVA activities, but IVA.
Okay, and how did you come up with like the whiteboard or the storage panels, those ideas?
Yeah, so our faculty advisor, Dr. Chamitoff, is actually a former astronaut himself. So it was really helpful to be able to talk to him, and we were able to brainstorm ideas and speak with an astronaut about, okay, would these kind of panel functionalities be useful, and how should we design these to better benefit someone completing, say, an experiment like protein crystal growth or completing a connector maintenance task. And he was really able to advise us and guide us about what some of the most useful capabilities for the HoloLens and AR in general would be on the ISS.
Right, and one of his comments about saying during some of his experiments on the space station, he had to look at a very long connector number and try to find that wire and connect it to the right connector. And we thought having some sort of, instead of just listening to an audio of someone in mission control saying, find connector 5A6 something, 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 it'd be good if they could actually draw and circle which one it would be, so that they don't have to, the astronaut doesn't have to memorize what number it is. So there's some visual feedback to that.
That's great. So with these different projects, how did you divide up the tasks?
So some of our team members didn't have any experience working in Unity, so they were doing more research-based portion of this, researching activities such as growing protein crystals and finding models and doing a lot of the baseline work that we really needed to start developing this. And then others of us who had a bit more Unity or other game engine experience really took on editing these UI panels and integrating all of these elements into developing the work for our demos. So we kind of split it up into a research side and a technical side.
Okay. And I noticed you're all different majors. So how was it working together with the different majors?
Yes, it's very reflective of the real world where we're able to bounce ideas off each other with this kind of multidisciplinary team. We have aerospace engineers and mechanical engineers and computer science engineers. So we were really able to bring a lot of different perspectives to the project and be able to think about things from multiple viewpoints and work on finding the best solution using all of our diverse backgrounds.
Okay, we've got a couple questions here now. So with the AR, does this improve task time that you found or tested?
Yes, the central design of these panels revolves around saving crew time. Currently, while completing tasks on the ISS, crew will use either voice loops or iPads. for kind of tasks. So the whole purpose of these panels is to save time referring back to voice loops or relying on referring back to iPads. And instead, you'll be able to have these panels directly in the field of vision, allowing you to keep that task list up while completing your work, which saves time iterating through different procedures or communicating back and forth between ground, because they can directly draw in your field of view instead of having to direct you through voice loops. So these panels are really meant to save time referencing different resources and allow you to quickly complete these tasks by keeping that procedure front and center. And in addition, like with the maintenance panel, the interactable 3D models provide visual cues that are very useful. Instead of trying to remember a part name and determining what part you should be looking for, you can quickly pull those up. You can open up, say you're working on a very small connector, you can pull that out of the diagram panel and toggle and rotate and expand the view so that you can more easily determine how to best proceed.
Okay, great. We have a couple more questions here. So does intense lighting or darkness impact how your panels will display?
No, these should display well in all lighting scenarios.
All right, and next question, how much training would an astronaut need to properly take advantage of this technology?
Yeah, so astronauts in general, right before they go aboard the ISS, complete several years of training on these different task procedures that they'd be completing. So ideally, they could integrate this with some of the VR and AR training that they're currently using. So this could be part of the training procedures that they're already completing, so that whilst they're aboard the ISS, this technology is already familiar to them and they've been using it while they've been completing training before going aboard the ISS.
Have any of these technologies already been used with AR on the station or shuttle or other things?
The HoloLens is, and AR is in use currently, but we were really looking to develop a lot of this technology. Our NASA mentor, Lei Wang, showed us some ideas for AR technology that he had been working on, talking about storage panels, and those had been about those had not included the diagrams that we include in our storage panel. And those are more for inventorying and scanning, and you can scan codes and database into the storage panels, whereas ours is really more for time completion and task completion, and being able to quickly pull up models of things in storage and be able to kind of expand those views and find those 3D models quickly so you can scan more than one bag at a quicker pace. So this technology has been developed a bit, but we've really wanted to expand upon what's been done and think about how we can save crew time further.
All right, and we got another question here. Safety during experimentation is important. Can you elaborate on how experimental safety fits into your design?
Yeah, so the safety procedures and any safety precautions could definitely be included in these experiment panels. In addition, as part of the safety includes reduction of distraction in field of vision. So say there's something that you need your whole field of vision for, those panels can be rotated and moved, and there's also different size panels, so you can choose so that nothing is blocking your field of vision, or you can have them pulled up directly in the field of vision so that you can see a 3D model of something, say maybe microscopic you're working on. So yeah, there's definitely safety precautions that could be uploaded into those panels, and as well in terms of, say you need your whole field of vision for safety purposes, and nothing blocking or distracting you, that's taken into account as well.
Okay, great. Any final thoughts from the other team members? What were some of your challenges or greatest successes this semester?
We were a one semester project, so this was really a tight deadline, and I think we're very proud of being able to accomplish our goals that we had set out. We were able to film complete demos for all of our panels and whiteboard functionality. So I think we're very happy with the progress that we were able to complete this semester.
And I'd like to add on, we wanted to test some of the AR functionality in person with the HoloLens or HoloLens 2, because we did in our lab at Texas A&M, we had some basic mock-ups of different connectors and mock science experiments that we could try to test out. But since we haven't been able to go back in the lab and actually see if how test out things like how big should the tasks be, or how well does this actually work, that's something we'd like to continue with when we can actually meet in person again. And we can probably do some of that on our own at home too, but it'll just be one person with the device. But to fix that, we just made pretty much a virtual simulation of our AR design, and we were still able to test things out and show the concept pretty well with that.
All right, great. Thank you very much, team.
Thank you.
Thank you.
Thank you.
All right, so this ends day one of our design showcase. Thank you all to the teams and their faculty advisors, NASA mentors, all their collaborators, which I'm sure helped quite a bit. We do have judges out there judging the videos and the posters. Thanks to them and everyone on the showcase audience, especially those who stuck with us from the beginning to the end here today. Please do come back tomorrow and we'll get to hear from another 10 teams. And finally, thank you and congratulations to all the students. You did phenomenal work this semester. All the questions that you got on Slido will be sent to you so you can incorporate those into your final report. We're also going to post all the videos on our YouTube channel, the individual videos, as well as the recording of this entire session with the Q&A. So you will be able to go back and review those as well. So if you do go to the YouTube channel, please subscribe, and hopefully we can get enough subscribers to give it a nice name like Design Challenge. For general questions, again, on the lower left of your screen, email showcase2020@tsgc.utexas.edu. We can give you the meet and greet links for the 10 teams today. They're going to have a relaxing meet and greet from 5 to 7. You need to bring your own beverage and snacks, but this is a relaxing time to meet the teams, get to know more about their projects. Students, I encourage you to go visit other teams and get some ideas. Try to get the most out of the meet and greet event. All right, finally, thank you for watching. Thanks also to Talia Jurgens and Angelica Cruzinga for helping run today's showcase. We will start tomorrow at noon Central Time with our opening speaker. And to learn more about Design Challenge, go to tsgc.utexas.edu/challenge. So whether you're brand new or a veteran attendee, thank you for attending Showcase, and we hope to see you tomorrow.